Welcome to the Late Lab. It's lovely to have you here. Before we begin, let the night settle around you for a moment. Maybe you're watching from a quiet room with the lights turned low, or from beneath a blanket that has become, for scientific purposes, an advanced personal climate system. Maybe there's a warm drink nearby, slowly cooling beside you, performing a tiny demonstration of thermodynamics without asking for applause. Wherever you are tonight, I hope you feel calm, comfortable, and ready to drift gently into one of the strangest simple questions the universe can offer. If you enjoy these slow scientific wanderings and would like more of them, a like and subscribe really does help this sleepy little channel keep glowing softly in the dark. And if you're already subscribed, thank you. Truly, your support helps more than you know. Now, tonight's subject may sound ordinary at first. Temperature. Warm things, cold things. The familiar little drama of tea going lukewarm when nobody asked it to. But taken seriously, temperature leads us all the way from the atoms trembling quietly inside matter to the afterglow of the Big Bang, still stretched across space after billions of years. So an apology in advance if this becomes just interesting enough to keep a small corner of your mind awake. At least, by the end, you may know why empty space is not quite empty, why the universe has been cooling for almost its entire history, and why even the deepest dark still carries a faint memory of heat. So let's begin, shall we? Why does the universe have a temperature? And what exactly is still warm out there in all that cold? Temperature is one of those ideas that feels simple because the body understands it before the mind begins to explain it. A warm mug rests between your hands. A cold window gathers the night on its glass. A blanket slowly becomes friendlier as it traps the warmth escaping from your body. The world is constantly offering these small lessons in heat and cold, and most of the time, no one needs to think about them too carefully. Warm soup is warm. Ice is cold. A radiator is doing its best. A bare foot on a tiled floor at midnight is a personal betrayal. But the moment temperature is followed beyond the everyday, it begins to change shape. It stops being just a sensation and becomes a question. Not only why does this object feel warm, or why does that surface feel cold, but why does anything have a temperature at all? And stranger still, how can the universe have one? How can something as vast as space, with its scattered galaxies and enormous stretches of apparent emptiness, be described as hot, cold, warming, cooling, or glowing with any measurable thermal history? At first, it is tempting to imagine temperature as some invisible ingredient inside matter, as though warmth were a substance poured into things. A hot stone seems to contain heat. A cold stone seems to lack it. For a long time, ideas about heat moved in that direction. Some 18th century thinkers imagined heat as a kind of subtle fluid called caloric, which flowed from hotter objects into colder ones. It was not a foolish idea. Heat does appear to move. A fire warms a room. A hand loses warmth to snow. Tea cools in the open air despite having committed no crime. Modern physics gives a more precise answer. Temperature is not a material hidden inside an object. It is a measure connected to energy and motion. In ordinary matter, temperature describes the average thermal energy of particles such as atoms and molecules. These particles are not still. In a solid, they vibrate around fixed positions. In a liquid, they move and slide past one another. In a gas, they travel more freely, colliding and scattering in restless patterns. When something is hotter, its particles generally have more average kinetic energy. When something is colder, they have less. That simple idea is much larger than it first appears. The same principle that helps explain a cooling drink also helps explain the temperature of a gas cloud between stars. It helps describe the surface of the sun, the atmosphere of Earth, the cold shadows on the moon, and the faint radiation left from the early universe. Temperature is not only a domestic fact of kettles, quilts, and questionable central heating. It is one of the basic ways science reads energy in nature. Still, the universe does not have a temperature in the same way a bedroom has a temperature. There is no single cosmic room, no universal thermostat, no polite little dial set somewhere behind a galaxy cluster. The universe contains many temperatures at once. The core of the Sun reaches roughly 15 million Kelvin, where nuclear fusion turns hydrogen into helium. Its visible surface is far cooler, around 5,700 Kelvin, though still rather inconvenient for sitting down. Thin gas between galaxies can be extremely hot in terms of particle energy, even while being so sparse that it would not feel hot in any familiar sense. Distant icy worlds can sit in deep cold. Black holes can be associated with temperature through the strange work of Jacob Bekenstein and Stephen Hawking, though large black holes have temperatures so tiny that they are colder than the radiation around them. So when science talks about the temperature of the universe, it is not saying that everything in existence is settled to one neat average warmth. The universe is not a bath, and space is not lukewarm soup. Instead, temperature becomes a way of describing different forms of energy in different cosmic settings. Matter has temperature. Radiation can have temperature. Gas clouds, stars, planets, and even the large-scale background of the universe can be understood through thermal behavior. The most important example is the cosmic microwave background, often called the CMB. This is the faint afterglow of the early universe. It is ancient light released when the universe first became transparent, roughly 380,000 years after the Big Bang. Before that time, space was filled with hot plasma, a dense glowing mixture where electrons and atomic nuclei were not yet joined into neutral atoms. Light could not travel freely for long because it kept scattering off charged particles, like beams trying to cross a thick glowing fog. As the universe expanded, it cooled. Eventually, electrons joined with nuclei to form mostly hydrogen and helium atoms. Once that happened, light could move through space much more freely. That ancient light is still travelling today, but the expansion of space has stretched it enormously. Its wavelengths have grown longer, and its energy has dropped. What began as a hot glow from the young universe is now detected as microwave radiation, with a temperature of about 2.7 Kelvin, only a little above absolute zero. This is why the idea of cosmic temperature is so powerful. It tells us that empty space is not simply nothing. Space can be astonishingly empty compared with anything on Earth, but it still contains radiation, rare particles, fields, cosmic rays, neutrinos, and the lingering microwave glow of the early cosmos. Even in the deep dark between galaxies, there is a measurable background left behind by the universe's hot beginning. When cosmologists say the universe is cooling, they are not claiming that every object everywhere is becoming colder at the same pace. Stars still form, gas still heats as gravity pulls it inward. Supernovae still release enormous energy. Planets absorb sunlight. Local heat continues to appear wherever energy is concentrated and transformed. But on the larger scale, the background radiation of the universe has cooled as space has expanded. The universe has not lost heat into some outside emptiness. There is no outside container waiting to receive it. Instead, expanding space stretches light itself, lowering the energy of the radiation that fills the cosmos. So the temperature of the universe is not one simple room temperature. It is a history written in motion, radiation, matter, and expansion. It describes particles trembling in ordinary objects, light stretched across billions of years, stars burning in galaxies, gas drifting through darkness, and the faint afterglow still arriving from the edge of the observable past. A small warm cup beside the bed and the great cooling universe outside are not separate stories. They are different scales of the same deep idea. Temperature is what happens when energy has a form, when matter moves, when light travels, when the past leaves a trace. And in that sense, the universe has a temperature because it has never been still. Heat feels almost magical because it arrives through the senses so quickly. A warm breeze touches the skin, and the body understands before any thought forms. A kettle hums, a radiator glows faintly, a bowl of soup sends steam into the air, and all of it seems to carry a hidden quality, called warmth. But underneath that familiar feeling, there is no spell, no secret fire fluid, no tiny invisible blanket tucked inside matter. Heat's motion. Temperature is the way that motion is measured. At the deepest ordinary level, the objects around you are built from atoms and molecules, and those atoms and molecules are rarely still. Even a quiet wooden table, a sleeping stone, or an ice cube sitting with great dignity in a glass is full of activity. In a solid, particles are usually held in place by bonds, so they do not wander freely through the material. But they still vibrate. They tremble around their positions like tiny restless bells that cannot quite leave where they are. The object may look calm, but inside it there is constant motion. In a liquid, the movement becomes more flowing. Molecules remain close together, but they can slide, turn, jostle, and rearrange themselves. This is why water can pour, ripple, and swirl. Its molecules are not locked into a rigid pattern. They're held together enough to remain a liquid, but free enough to move past one another. A glass of water resting on a bedside table may look perfectly peaceful, but at the molecular level it is a crowded dance floor, just one with very strict rules and no embarrassing music. In a gas, the particles are freer still. Air molecules travel in straightish paths until they collide with one another, or with the walls of a room, a balloon, or a lung. They move at different speeds, in different directions, constantly exchanging energy through collisions. Warm air generally means that these molecules have more average kinetic energy. Cold air means they have less. Kinetic energy is the energy of motion, and it is one of the central ideas behind temperature. This particle-level view is described by kinetic theory, the scientific framework that connects the behavior of gases and matter to the motion of their microscopic parts. In the 19th century, James Clerk Maxwell helped describe how gas particles move at a range of speeds, rather than all travelling identically. Ludwig Boltzmann developed the statistical ideas that link the microscopic world of particles with the large-scale properties we can measure, such as temperature and pressure. Together, their work helped show that heat was not a mysterious substance drifting through matter, but a pattern emerging from enormous numbers of moving particles. The important word here is average. Temperature does not usually tell us the exact motion of every particle. In even a small amount of air, there are far too many molecules to track one by one. Instead, temperature describes the average thermal energy of the particles in a system. Some particles are moving faster, some slower. Some collide and gain energy, others collide and lose it. But when enough particles are considered together, a meaningful pattern appears. That pattern is what thermometers help us read. This is why hotter objects generally contain particles moving with greater average kinetic energy, while colder objects contain particles with less. The phrase generally matters, because different materials store and share energy in different ways. A piece of metal and a piece of wood at the same temperature can feel very different to the hand, because metal conducts heat away from skin much more efficiently. The metal is not necessarily colder. It is simply better at stealing warmth, which is rude, but scientifically impressive. Warm air offers a gentle example. When air is heated, its molecules move more energetically on average. They collide more forcefully and spread apart more easily, which is why warm air tends to become less dense and rise. Boiling water gives another example. As water is heated, its molecules move more vigorously, until some gain enough energy to escape the liquid as vapour. Steam is not water becoming mystical. It is water molecules gaining enough freedom to wander off, like tiny commuters leaving a crowded station. Cold metal feels different, but the same principle applies. Its atoms are still vibrating, just with less average thermal energy than they would have at a higher temperature. The metal may feel sharply cold because it conducts heat quickly away from the warmer hand. Solid ice is colder still, yet even there motion remains. The water molecules in ice are arranged in a crystal structure, held in place by bonds, but they still vibrate. Ice is not perfectly motionless, it is a rigid pattern, with a faint internal shiver. This matters because temperature is easy to misunderstand when nothing appears to be moving. A block of stone looks still. A frozen lake looks still. The air in a quiet room seems still until dust crosses a shaft of light and reveals subtle currents. But apparent stillness is not microscopic stillness. Matter is active at scales too small for human senses to notice directly. The calm surface of the world is built from restless ingredients. In space, this becomes harder to picture. On Earth, temperature is usually felt through contact with matter. Air touches skin. Water carries heat. A chair feels cold or warm because energy moves between the chair and the body. But space often contains very few particles. In the emptiest regions between stars and galaxies, matter can be spread so thinly that ordinary ideas of hot and cold become less intuitive. There may be particles with high energies, meaning a very high temperature in one scientific sense, but so few of them that they would not warm an object very effectively. This is why cold space is more complicated than it sounds. A spacecraft in sunlight can become hot because it absorbs radiation from the sun. The same spacecraft in shadow can cool by radiating energy away. Since there is very little air in space, there is little conduction or convection, the processes that normally carry heat through touch and fluid motion. In vacuum, radiation becomes the main way heat is gained or lost. Space is not cold like a freezer full of air. It is cold like an immense absence that allows objects to lose energy into darkness, unless something bright is shining on them. Once temperature is understood as motion, energy, and distribution, the idea can travel outward without breaking. A nebula has temperature because its gas particles move and collide. A star has temperature because its plasma is filled with intensely energetic particles and radiation. Plasma, the state of matter found in stars and the early universe, is made of charged particles moving freely enough that electrons are separated from atomic nuclei. Radiation can also be described by temperature when it has the right kind of thermal spectrum, as with the cosmic microwave background. So heat is not magic. It is motion made meaningful by numbers. It is the trembling of atoms, the wandering of molecules, the rushing of gas, the boiling of water, the vibration inside ice, the glow of plasma, and the fading afterglow of the early universe. The same idea stretches from the warmth of air in a quiet room to the hot gas of nebulae and the ancient radiation still crossing space. Temperature is not a thing hidden inside the universe. It is one of the ways the universe reveals that, at every scale, it is moving. To measure temperature across the universe, ordinary language begins to struggle a little. Hot, cold, warm, chilly, freezing, boiling. These words are useful in daily life, especially when deciding whether to touch a mug, open a window, or retreat heroically from a cold bathroom floor. But the universe is not very interested in human comfort. It contains star cores, frozen moons, thin gas clouds, laboratory condensates, glowing plasma, black holes, and ancient radiation stretched across nearly all observable space. To describe all of that, science needs a temperature scale that does not begin with water, weather, or whether a person has remembered their socks. That scale is Kelvin. The Kelvin scale is the temperature scale most useful in physics because it begins at absolute zero. Absolute zero is 0 Kelvin, the theoretical lower limit of temperature. It represents the point where a system has the lowest thermal energy allowed by physics. In simple terms, it is as cold can meaningfully get. There is no cold or ordinary temperature below it, because temperature is connected to particle motion and energy, and absolute zero marks the lower boundary of that thermal motion. This does not mean that everything becomes perfectly dead and motionless in the simplest imaginable way. That older picture is tempting, because if heat is motion, then no heat sounds like no motion at all. But quantum mechanics makes the story subtler. Particles are not tiny billiard balls that can simply be brought to a perfect halt. Quantum systems retain what is called zero-point energy, the lowest possible energy they can have. So absolute zero is not a magical switch that turns the microscopic universe into a frozen photograph. It is the lowest thermal state a system can reach, while quantum behavior still prevents the neat idea of complete classical stillness. The Kelvin scale is named after William Thomson, better known as Lord Kelvin. In the 19th century, Thomson helped formalize an absolute temperature scale rooted in thermodynamics, the science of heat, energy, work, and physical change. His work was part of a much wider transformation in physics, when heat was being understood less as a mysterious fluid and more as a measurable feature of energy and matter. An absolute scale mattered, because it gave scientists a way to talk about temperature from a physical foundation, rather than from the habits of ordinary life. The Celsius scale is still useful, of course. It is wonderfully practical. 0 degrees Celsius marks the freezing point of water under standard conditions, and 100 degrees Celsius marks the boiling point of water under standard conditions. That makes it very handy for weather, cooking, icy pavements, and the dramatic moment when tea becomes too dangerous to sip. Celsius is tied to water, and water is deeply important on Earth. But the universe is not mostly a kitchen, inconvenient as that may be for anyone hoping the cosmos came with snacks. Kelvin is more fundamental because it starts at absolute zero. A change of 1 Kelvin is the same size as a change of 1 degree Celsius, but the starting point is different. 0 degrees Celsius is the freezing point of water. 0 Kelvin is the lower limit of thermal temperature itself. In Celsius terms, 0 Kelvin is about minus 273 degrees Celsius. That is not merely cold in the everyday sense. That is cold so deep that ordinary winter has no useful opinion about it. Some reference points help make Kelvin feel less abstract. A comfortable room is roughly 293 Kelvin, depending on the room, the season, and the mysterious habits of whoever controls the heating. Water freezes at about 273 Kelvin. Liquid nitrogen is about 77 Kelvin, cold enough to make many materials behave in surprising and brittle ways. The cosmic microwave background, the faint afterglow from the early universe, is about 2.7 Kelvin. That is only a little above absolute zero, yet it fills the universe as a measurable background of ancient radiation. At the other end of the scale, stars take Kelvin into far larger numbers. The visible surface of the Sun is about 5,700 Kelvin. Hotter blue stars can have surface temperatures of tens of thousands of Kelvin. Deep inside stars, where nuclear fusion occurs, temperatures can reach millions of Kelvin. The Sun's core is roughly 15 million Kelvin, where hydrogen nuclei have enough energy under immense pressure for fusion to produce helium and release light and heat. Kelvin can describe both the faint chill of cosmic background radiation and the furious plasma inside a star. This is one of its great strengths. The scale also helps scientists compare environments that would be difficult to place side by side in ordinary speech. A cold molecular cloud in space might be only 10 or 20 Kelvin, cold enough for atoms and molecules to move sluggishly, allowing complex chemistry to unfold in dark regions where stars may eventually form. A laboratory experiment using ultra-cold atoms might reach temperatures far below 1 Kelvin, approaching absolute zero with extraordinary precision. A galaxy cluster can contain thin plasma at tens of millions of Kelvin, even though the gas is so spread out that it would not feel hot in any everyday way. Kelvin gives all of these conditions a shared language. That shared language is essential because cosmic temperature is not about comfort. It is about energy. It asks how particles move, how radiation behaves, how matter changes state, and how physical systems evolve. It lets scientists describe the warmth of a planet, the colour of a star, the cooling of the early universe, the faint microwave glow crossing space, and the behaviour of matter near the limits of laboratory physics. Without an absolute scale, these comparisons would become clumsy very quickly, like trying to describe an orchestra using only the words loud, quiet, and please stop giving the trombone ideas. The Kelvin scale also connects naturally to the story of the expanding universe. When cosmologists say the cosmic microwave background has a temperature of about 2.7 Kelvin, they're not saying it feels like cold air. There is almost no air in deep space. They are describing the energy distribution of radiation that once filled the young universe as a much hotter glow. As space expanded, the wavelengths of that light stretched, its energy dropped, and its temperature fell. Kelvin allows that cooling to be measured in a way that fits both thermodynamics and cosmology. So Kelvin is more than a scientific preference. It is a way of giving temperature a physical anchor. Celsius begins with water, which is lovely and useful and makes a fine cup of tea possible. Kelvin begins with the lowest thermal energy nature allows. That makes it the scale of star cores and cold gas clouds, of liquid nitrogen and quantum laboratories, of frozen worlds and the cosmic microwave background. It reaches from the almost familiar to the almost unimaginable. And that is why the universe's temperature is measured in Kelvin. Not because the universe is one enormous object with one simple warmth, but because Kelvin gives science a scale wide and steady enough to hold the whole thermal story. From absolute zero to stellar fire, from the quiet cold between galaxies to the ancient afterglow of the Big Bang, it lets temperature become not just a feeling, but a map of energy across reality. Thermodynamics is the science of heat, energy, work, and the quiet rules that decide which way physical processes naturally unfold. It explains why a hot drink cools in a room, why an engine cannot turn every bit of heat into useful motion, why stars shine for so long, and why the universe seems to have a direction in time. It is, in a sense, cosmic accounting. Energy can move. Energy can change form. Energy can be stored, released, concentrated, scattered, hidden in motion, or carried away as light. But it always has to be accounted for. The roots of thermodynamics grew from very practical questions. In the early 19th century, Sadi Carnot studied heat engines and asked how efficiently heat could be turned into work. His ideas were developed during an age of steam engines, coal, pistons, factories and machinery that was often loud enough to make a peaceful nap seem like a radical political act. But behind the machinery was a deep question. What is heat actually doing when it makes something move? James Prescott Joule helped show that heat and mechanical work were connected forms of energy. His experiments demonstrated that motion could produce heat in measurable ways, helping establish the idea that energy is conserved. Rudolf Clausius later gave thermodynamics some of its most important language, including the concept of entropy. William Thomson, known as Lord Kelvin, helped place temperature on an absolute scale and contributed deeply to the understanding of heat, energy, and physical limits. Together, these thinkers helped turn heat from an everyday sensation into one of the great organizing principles of physics. The first law of thermodynamics is the law of energy conservation. It says that energy cannot simply appear from nothing or vanish into nothing. It can change form, and it often does. Chemical energy in wood becomes heat and light in a fire. Electrical energy becomes light in a lamp. The nuclear energy in the sun's core becomes radiation that eventually warms planets. A falling object turns gravitational potential energy into motion, and that motion may later become heat through friction. The details can be complicated, but the principle is steady. Energy changes its costume, not its existence. This matters for cosmic temperature because the universe is filled with transformations of energy. Gravity pulls gas together, and the gas heats as it compresses. Stars convert nuclear energy into light and heat through fusion. Planets absorb radiation and emit infrared light back into space. Supernovae throw energy into surrounding gas. Black holes can heat nearby matter as it spirals inward. Even the cosmic microwave background carries energy from the early universe, stretched and cooled by the expansion of space. Thermodynamics is the ledger beneath all these changes. The second law of thermodynamics adds something even stranger. It says that in an isolated system, entropy tends to increase. This is often described as disorder increasing, but that phrase can be misleading if it is left alone too long. Entropy is not just messiness, and it is not really about whether socks are on the floor, although the floor may wish to file a complaint. In physics, entropy is a statistical measure connected to how many microscopic arrangements can produce the same overall state. A tidy stack of papers has relatively few arrangements that still look like a tidy stack. A scattered pile has many more arrangements that still look scattered. In a similar way, energy concentrated in one place can often spread out into many possible microscopic arrangements. A hot object beside a cold one contains a sharp temperature difference. Over time, heat flows from the hotter object to the colder object, until their temperatures become more even. The final state has energy more widely distributed, and there are many more microscopic ways for that even distribution to occur. This is why heat naturally flows from hot to cold. Not because cold pulls heat with tiny invisible hands, but because spreading energy out is overwhelmingly more statistically likely than having it gather itself back into one neat concentration. A warm mug cools because energy moves into the cooler surrounding air and surfaces. The room warms by a tiny amount, the drink cools by a noticeable one, and the combined system moves toward a more even distribution of thermal energy. The tea does not later gather that same warmth back from the room and reheat itself, though many people would support this feature if physics accepted suggestions. The second law also gives time a kind of arrow. Many physical laws work almost as well forwards or backwards on paper, but thermodynamics makes the lived universe feel directional. Ice melts in a warm room. It does not usually unmelt by gathering heat from puddles and rebuilding itself into cubes. Perfume spreads through air. It does not naturally collect itself back into the bottle. Stars burn through fuel. They do not quietly reassemble spent radiation into fresh hydrogen and politely start again. At the scale of the universe, entropy becomes one of the deepest ideas in cosmology. The early universe was extremely hot and dense, but also, in an important gravitational sense, very smooth. Over time, gravity gathered matter into stars, galaxies, and clusters. This created local pockets of structure and heat. But the wider thermodynamic story still involves energy spreading, radiation cooling, stars exhausting their fuel, and usable temperature differences becoming harder to maintain over immense timescales. This leads to the idea of heat death, one possible far future of the universe. Heat death does not mean everything catches fire, and it does not mean the universe suddenly freezes like a dramatic scene in a science fiction film. It means a state in which useful energy differences have mostly evened out. If there are no strong temperature differences left, there is little available energy to do work. Stars would have faded. New star formation would have dwindled. Matter would be thinly spread. Radiation would be stretched to extremely low energies. The universe would still exist, but it would have fewer ways to change in lively, organized forms. That future is unimaginably distant, and many details depend on long-term cosmology, dark energy, black holes, and particle physics. But the basic thermodynamic idea is clear. Temperature is not only about how hot something feels, it is about how energy is arranged and whether differences exist that can drive change. A star shines because energy moves from a hotter interior toward cooler space. A planet has weather because sunlight, atmosphere, rotation, oceans, and surface temperatures create flows and contrasts. Life itself depends on energy gradients, taking in useful energy and releasing waste heat, like a tiny thermodynamic negotiation conducted by cells. So cosmic temperature is part of a larger story about energy distribution. It connects the warmth of a hand, the cooling of tea, the glow of stars, the expansion of space, the fading of ancient radiation, and the possible long sleep of the universe. Thermodynamics is the science that explains why heat moves, why energy changes form, why some processes unfold naturally in one direction, and why the universe has a past that looks different from its future. In that sense, thermodynamics is not just about engines, kettles, or laboratory equations. It is about the behavior of reality when energy is allowed to move. It is the quiet bookkeeping behind every flame, every orbiting world, every cooling cloud, every star, and every faint photon stretched by cosmic expansion. The universe has a temperature because it has energy. Thermodynamics tells us how that energy flows, spreads, transforms, and leaves behind the long, measurable history of heat. Temperature seems easiest to understand when there is matter involved. A hand touches a warm cup. Air moves across skin, water boils in a pan, metal glows in a forge. These are ordinary scenes where heat feels tied to atoms and molecules, to things with substance and texture. But the universe has a slightly stranger habit. It allows temperature to describe not only matter, but light as well. At first, that sounds odd. Light has no surface to touch. It does not sit still in a room waiting for a thermometer. A beam of sunlight crossing a curtain does not seem to have a temperature in the same way a stone or a bowl of soup does. Yet under the right conditions, radiation can be described by temperature. This happens when light is in thermal equilibrium with matter, meaning the radiation and the matter have interacted enough to share a common thermal state. In that situation, the light carries a very specific pattern of energies, and that pattern reveals the temperature. This idea is essential for understanding the early universe. Long before stars and planets existed, the young cosmos was filled with hot plasma, where charged particles and radiation constantly interacted. Photons, the particles of light, were repeatedly scattered, absorbed, and re-emitted. They did not travel freely through transparent space the way starlight does today. Instead, matter and radiation were tightly coupled, sharing a common temperature. The universe was not merely full of hot matter, it was filled with hot light. The key concept here is blackbody radiation. A blackbody is an idealized object that absorbs all radiation falling on it and emits radiation in a pattern determined only by its temperature. Real objects are never perfect blackbodies, but many come close enough for the idea to be extremely useful. A blackbody does not need to be black in the everyday sense. The name refers to how perfectly it absorbs incoming radiation. When heated, it glows according to a precise thermal spectrum. This glow was one of the great puzzles of 19th century physics. Scientists could measure how hot objects emitted light, but explaining the exact spectrum was difficult. Classical physics predicted results that did not match reality, especially at shorter wavelengths. This problem became known as the ultraviolet catastrophe, which is an excellent name for a physics problem and a terrible name for a relaxing holiday. In 1900, Max Planck found a solution by proposing that energy was emitted and absorbed in discrete packets rather than in any continuous amount. These packets would later be understood as part of the foundation of quantum theory. Planck's work explained the spectrum of blackbody radiation and showed that the colour and intensity of thermal light are deeply connected to temperature. His discovery did not merely solve a technical problem about glowing objects, it opened a door into quantum physics. The everyday world offers gentle examples of this relationship between temperature and light. A cool object, such as a person, a wall, or a warm mug, emits mostly infrared radiation. Infrared light is invisible to human eyes, but it can be detected as heat by thermal cameras. This is why a person can glow brightly in an infrared image while looking perfectly ordinary in visible light, apart from the usual human mystery of why one sock has disappeared. As an object becomes hotter, the radiation it emits shifts towards shorter wavelengths. A piece of metal heated in a fire may begin to glow dull red. With more heat, it can become orange, yellow, and eventually white hot. The colour is not random, it is a clue to the object's temperature. The same principle applies to stars. Cooler stars appear reddish, hotter stars can look blue-white. The Sun's visible surface, at roughly 5,700 Kelvin, emits strongly across visible light, which is why it appears essentially white from space, even though Earth's atmosphere can make it look yellowish or orange near sunrise and sunset. Astronomers use this connection between colour spectrum and temperature constantly. A star's surface temperature can be estimated by studying its spectrum, the detailed spread of light across different wavelengths. A spectrum is more informative than a simple colour, because it reveals how much light arrives at each wavelength. It can show temperature, chemical composition, motion, magnetic effects, and other physical details. Light is not just brightness, it is information travelling across space. Planck's law describes the exact shape of blackbody radiation. The mathematical form does not need to be carried around like heavy luggage, but the idea is clear. A blackbody at a given temperature emits a characteristic spectrum. Cooler blackbodies peak at longer wavelengths. Hotter blackbodies peak at shorter wavelengths. This means temperature can be read from the pattern of light itself. The universe, very helpfully, has been leaving thermal receipts everywhere. This becomes especially important with the cosmic microwave background, often called the CMB. The CMB is the faint radiation left from the early universe, released when space became transparent roughly 380,000 years after the Big Bang. Before that moment, radiation and matter were in thermal equilibrium. Photons scattered again and again through the hot plasma, sharing energy with charged particles. The light had the spectrum of a very hot blackbody. Then the universe expanded and cooled. Electrons joined with nuclei to form neutral atoms, and light could finally travel freely. Since that time, the expansion of space has stretched the wavelength of those ancient photons. Their energy has dropped, and the temperature associated with that radiation has fallen to about 2.7 Kelvin. Today, this radiation arrives mostly as microwaves, far colder and longer in wavelength than the glow it once had. One of the most remarkable facts in cosmology is that the cosmic microwave background is almost a perfect blackbody spectrum. Measurements by the NASA Cosmic Background Explorer, known as COBE, showed this with extraordinary precision. The result was a powerful confirmation that the early universe really was once hot, dense, and in a state where matter and radiation shared a common thermal history. The CMB is not just a faint hiss of microwaves, it is the cooled thermal glow of the young universe. So light can have a temperature when its energy follows the pattern of thermal radiation. This does not mean every stray beam of light has a simple temperature in the same way a cup of tea does. A laser, for example, is not blackbody radiation. Reflected sunlight is not automatically the temperature of the object reflecting it. But when radiation has been shaped by thermal equilibrium, its spectrum can carry temperature with exquisite precision. This is why the universe's temperature story cannot be told only through atoms and gas. It must also be told through light. Light reveals the heat of stars, the warmth of dust, the cooling of planets, and the ancient fire of the early cosmos. It crosses space as a messenger, carrying the memory of the conditions that created it. And in the cosmic microwave background, that memory is almost impossibly old. A blackbody glow stretched thin by expansion, still whispering that the universe was once far hotter than it is today. The phrase Big Bang can be a little misleading, because it sounds like a blast happening somewhere in darkness, as if the universe were a firework expanding into a larger empty room. But the Big Bang model does not describe matter exploding into pre-existing space. It describes space itself expanding from an earlier state that was much hotter and much denser than the universe we see today. The galaxies are not flying away from one central point in the way sparks fly from a bonfire. On the larger scales, the distance between galaxies is increasing because the fabric of space is stretching. This is one of the most important ideas in modern cosmology. The universe was once smaller, denser, hotter, and filled with radiation and matter in a state very different from the calm night sky we see above us. Not quieter, not emptier, and certainly not tidier. The early universe was not a peaceful black emptiness waiting for stars to arrive. It was a hot, dense, glowing environment where particles and light were crowded together, interacting constantly. One of the key figures behind this picture was Georges Lemaitre, a Belgian priest, physicist, and cosmologist. In the 1920s, Lemaitre proposed that the universe was expanding and had evolved from a much denser earlier state. His work was bold, because the idea of a changing universe was not yet comfortable for everyone. A universe that expanded also seemed to imply a history. It suggested that if the cosmic expansion were traced backward, the universe would become denser, hotter, and more compressed. Observational support came from the work of Edwin Hubble, building partly on earlier redshift measurements by Vesto Slipher. Hubble's observations of distant galaxies showed that, in general, galaxies farther away appear to be receding faster. Their light is stretched toward longer, redder wavelengths. This relationship became one of the great clues that the universe is expanding. It did not mean Earth sat at a special centre. Instead, it meant that space itself was growing, so distant galaxies were becoming more distant from one another across cosmic time. If the universe is expanding now, then in the past it was more compact. And if the same matter and radiation were packed into a smaller cosmic volume, the temperature would have been much higher. This is the thermal heart of the Big Bang model. The universe began, as far as current evidence can trace it, in an extremely hot and dense state. Not a fireball sitting in space, but a hot, dense universe everywhere. In its early stages, the universe was filled with plasma. Plasma is a state of matter in which electrons are separated from atomic nuclei, creating a mixture of charged particles. It is sometimes called the fourth state of matter, alongside solids, liquids, and gases, although stars would probably argue that plasma deserves rather more attention. The sun is made mostly of plasma. Lightning contains plasma. The early universe, before ordinary atoms could form, was also a plasma. This matters because plasma interacts strongly with light. Free electrons scatter photons, which are particles of light. In the young universe, photons could not simply travel across space in long, straight paths, the way light from distant galaxies travels today. Instead, light was constantly being scattered by charged particles. A photon would move a short distance, meet an electron, scatter, move again, scatter again, and continue in this restless pattern. The universe was glowing, but it was not transparent. A useful image is a thick fog, though an extremely hot and energetic one. In ordinary fog, water droplets scatter visible light, making distant objects hard to see. In the early universe, free charged particles scattered photons, making the cosmos opaque. Light existed everywhere, but it could not travel freely for great distances. There were no clear views across space, no stars shining through darkness, and no galaxies separated by transparent emptiness. The universe was more like a dense luminous mist, filled with radiation and matter-sharing energy. The temperatures involved were enormous compared with anything familiar, in the earliest moments that physics can describe with some confidence. Particles had energies far beyond those inside stars today. As the universe aged and expanded, it cooled through many stages. Protons and neutrons formed. Light atomic nuclei formed in a process called Big Bang nucleosynthesis. Much later, electrons joined nuclei to form neutral atoms. Each step depended on temperature falling enough for new structures to survive without being immediately broken apart by energetic radiation. This is a crucial point. The early universe was not simply hot because something had heated it from outside. There was no outside furnace. Its temperature came from the density and energy of matter and radiation packed into a much smaller volume. Particles collided with tremendous energies. Photons were far more energetic than the microwave photons filling space today. Everything was crowded, intense, and tightly coupled. The universe was young, dense, bright, and almost unimaginably hot. Then expansion changed everything. As space expanded, matter became more spread out. Radiation was stretched to longer wavelengths. Longer wavelength light carries less energy, so the temperature of the radiation fell. The universe did not cool by pouring heat into some surrounding void, because there is no larger room outside the universe in that simple sense. It cooled because expansion changed the conditions inside the universe itself. Space stretched, radiation lost energy, particles became less crowded, and the cosmic environment moved through different physical states. This is why cosmic temperature is also a story of transformation. A hot plasma became a cooler plasma. A cooler plasma eventually allowed neutral atoms to form. Transparent space emerged from what had once been an opaque glow. Much later, gravity gathered matter into the first stars and galaxies. Local regions heated again as gas collapsed. Stars ignited and galaxies grew, but the large-scale background of the universe continued cooling. The Big Bang model is therefore not just a theory about cosmic beginnings. It is a theory about change. It explains why the universe has a thermal past, why the oldest light has cooled into microwaves, and why space today is thin, dark, and transparent rather than dense and glowing. The universe began hot and dense, then expanded, thinned, cooled, and changed form. So the question of why the universe has a temperature reaches back into this early state. Temperature was there when matter and radiation were packed together. It shaped when particles could form, when nuclei could survive, when atoms could appear, and when light could finally travel freely. The universe's temperature is not an added detail. It is part of the main story. The cosmos we see tonight, scattered with stars and quiet darkness, is what remains after the young universe stretched itself from a blazing fog into an expanding sea of space. The universe did not cool in the way a cup of tea cools on a table. A hot drink loses heat into the cooler room around it. Steam rises, warmth moves into the air, the mug, the table, and eventually the wider world, which is very committed to making tea less exciting over time. But the universe is not sitting inside a larger room. There is no outside space into which cosmic heat can simply leak away. The cooling of the universe is stranger than that. It is tied to the expansion of space itself. When space expands, the distances between faraway galaxies increase. This does not mean every object is being stretched apart locally. Atoms are not swelling. Planets are not gently inflating. The solar system is held together by gravity. And people are held together by rather important forces that do not need cosmology interfering with them. But on the larger scales, between galaxy clusters separated by immense distances, the fabric of space is expanding. As that happens, light travelling through the universe is stretched along with it. Light travels as electromagnetic waves, and those waves have wavelengths. A shorter wavelength means the light carries more energy. A longer wavelength means it carries less. In the early universe, the radiation filling space was extremely energetic. It was not the faint microwave glow observed today, but a hot bath of light interacting constantly with matter. As the universe expanded, the wavelengths of those photons were stretched. Their energy dropped. And because the temperature of thermal radiation is connected to the energy distribution of its photons, the radiation cooled. This stretching of light by the expansion of space is called cosmological redshift. The word redshift comes from the fact that visible red light has a longer wavelength than visible blue light. When light from distant galaxies is stretched toward longer wavelengths, it shifts toward the red end of the spectrum, and beyond it into infrared, microwave, and radio wavelengths if stretched enough. The name has stayed, even though cosmological redshift can affect all light, not just light human eyes can see. The history of this idea includes several important figures. Vesto Slipher measured the redshifts of many spiral nebulae, which were later understood as galaxies beyond the Milky Way. Georges Lemaitre connected the idea of an expanding universe with the behaviour of distant galaxies and proposed that the universe had evolved from a much denser earlier state. Edwin Hubble provided influential observational evidence that more distant galaxies tend to recede faster, helping establish cosmic expansion as a central feature of modern cosmology. The story is not the work of one person alone, but a gradual unfolding of measurement, mathematics, and interpretation. It is useful to separate cosmological redshift from the ordinary Doppler shift. Doppler shift happens when a source of waves moves relative to an observer through space. The familiar example is the sound of a passing siren. As the vehicle approaches, the sound waves are compressed, and the pitch seems higher. As it moves away, the waves are stretched and the pitch seems lower. Light can also be Doppler shifted when objects move toward or away from us. Cosmological redshift is different. It is not simply that a galaxy is moving through space, like a car driving away down a road. Instead, the space between us and that distant galaxy expands while the light is travelling. The light wave itself is stretched because the cosmic distance it crosses is stretching. The galaxy can be thought of as being carried along by expanding space, rather than merely speeding through a fixed background. This distinction matters because it helps avoid the mistaken picture of galaxies exploding outward from one central point. A gentle way to picture it is to imagine a pattern drawn on a soft fabric. If the fabric is stretched, the marks move farther apart, not because they are crawling across the surface, but because the surface itself is changing. Now imagine a wave pattern drawn across that fabric. As the fabric stretches, the distance between the crests of the wave also grows. The wave becomes longer. In the universe, the fabric is space, and the light wave travelling through it becomes stretched as space expands. For photons, this stretching has a real energetic consequence. A photon with a shorter wavelength carries more energy. A photon with a longer wavelength carries less. So as cosmic expansion stretches radiation, the photons lose energy. This is one of the great quiet facts of cosmology. The light from the early universe has been steadily softened by the growth of space. It began as high-energy radiation in a hot young cosmos, and after billions of years of expansion, it arrives as low-energy microwaves. This does not mean that energy has leaked into a surrounding void. There is no ordinary outside place into which the radiation has drained. In the framework of general relativity, energy in an expanding universe is more subtle than energy in a small closed box. The important physical point is that expansion changes the wavelength of the radiation, and that change lowers the energy of the photons. The cosmic cooling is not like a bathtub losing warmth into a cold bathroom. It is more like the universe stretching the notes of its own ancient light until the pitch becomes deeper and quieter. The cosmic microwave background is the clearest example. When the universe first became transparent, roughly 380,000 years after the Big Bang, the radiation filling space had a temperature of about 3,000 Kelvin. That light would have been far more energetic than it is now, closer to the glow of a hot surface than the faint microwave background observed today. But as the universe expanded, the wavelengths of those photons stretched by more than 1,000 times. Their temperature fell with them. Today, the cosmic microwave background has a temperature of about 2.7 Kelvin. It is almost unimaginably cold by ordinary standards, only a little above absolute zero. Yet it is also the cooled remnant of a once hot universe. Its present temperature is not arbitrary. It is the result of expansion acting across cosmic time. The light has not disappeared. It has faded into longer wavelengths, carrying with it a measurable record of how much the universe has stretched since that ancient transparent moment. This is why expansion and temperature are so closely linked. To understand why the universe has a temperature, it is not enough to know that matter moves or that radiation can glow. It is also necessary to understand that space itself changes the energy of light as the universe grows. The cosmos cools because its radiation is stretched. The background glow becomes colder because the universe becomes larger. The oldest light does not simply travel through history, it is altered by history. And so the dark between the stars is not just dark. It is filled with ancient radiation that has been lengthened, softened, and cooled by the expansion of space. Every microwave photon in the cosmic background is a small messenger from a hotter time, arriving now with less energy than it once had. The universe has been stretching its first visible light for billions of years, and the temperature we measure today is the quiet result of that immense unfolding. For hundreds of thousands of years after the Big Bang, the universe was bright, hot, and strangely impossible to see through. That may sound contradictory because brightness usually helps with seeing. A lamp makes a room visible. The sun lights the landscape. A phone screen at midnight lights the face in a way that is Frankly, not always flattering. But the early universe was different. It was full of light, yet it was not transparent. The reason was plasma. The young universe was filled with charged particles, mostly atomic nuclei, free electrons and photons. The nuclei were mainly hydrogen and helium nuclei, formed earlier during Big Bang nucleosynthesis. But for a long time, the universe was still too hot for electrons to settle into stable atoms. Whenever an electron tried to join a nucleus, energetic radiation could knock it loose again. Matter could not yet become the neutral atoms familiar today. This meant light could not travel freely. Photons were constantly scattered by free electrons. A photon might move a short distance, meet an electron, scatter away in a new direction, then repeat the process again and again. The universe was glowing, but it was also opaque, a little like a dense fog or a cloud lit from within. Light existed everywhere, but it could not cross great distances in straight lines. Space was not yet the clear dark window through which galaxies could one day be seen. Then, as the universe expanded, it cooled. Expansion stretched radiation to longer wavelengths and reduced its energy. Eventually, roughly 380,000 years after the Big Bang, the temperature fell low enough for electrons to join atomic nuclei and remain bound. This period is called recombination, although the name is slightly odd because it was really the first major formation of neutral atoms, not a reunion after an earlier breakup. Physics, like many old institutions, sometimes keeps names for historical reasons and asks everyone to be polite about it. During recombination, electrons combined with protons to form neutral hydrogen atoms. Some electrons also joined helium nuclei to form neutral helium. These atoms did not carry the same free electric charge as the earlier plasma, so they interacted with light much less strongly. The fog began to clear, not because the universe suddenly became empty, but because the particles that had been scattering light so efficiently were no longer roaming freely in the same way. This change allowed photon decoupling. Photon decoupling means that light stopped being constantly scattered by charged particles and began travelling across the universe almost undisturbed. Recombination describes the formation of neutral atoms. Photon decoupling describes the release of light from the constant scattering that had trapped it in the glowing plasma. The two events are closely linked and happened around the same era, but they describe slightly different parts of the story. The moment was not like a curtain snapping open everywhere at once in a single instant. It was more like a transition, a gradual clearing as the universe cooled enough for neutral atoms to become common. But on cosmic timescales it marked a profound change. Before it, the universe was opaque. After it, the universe became transparent to most of that radiation. Light could finally travel across space for vast distances, carrying with it information from the time when it last scattered from matter. That ancient released light is what is now observed as the cosmic microwave background, often called the CMB. At the time of decoupling, the radiation had a temperature of about 3000 Kelvin, similar to the glow of a warm reddish surface. But it has not remained at that temperature. As the universe expanded over billions of years, the wavelengths of those photons stretched enormously. Their energy dropped and their temperature fell. Today, that same radiation is seen as microwaves, with a temperature of about 2.7 Kelvin. This is one of the most beautiful connections in cosmology. The cosmic microwave background is not light from stars. It is older than the first stars. It is not a glow produced by galaxies. It comes from a time before galaxies had formed. It is the leftover radiation from the moment the universe became transparent, the earliest light that can be observed directly across the whole sky. When astronomers study it, they are not seeing the beginning itself, but they are seeing a kind of surface of last scattering. the place in time when photons last interacted strongly with ordinary matter before travelling freely. The idea that such relic radiation should exist was predicted before it was discovered. Ralph Alpher and Robert Herman, building on work connected with George Gamow, argued in the late 1940s that a hot early universe should have left behind a cooled background of radiation. Their prediction was an important part of Big Bang cosmology. If the universe had once been hot and dense, then some remnant of that heat should still be detectable, stretched, and cooled by expansion. That prediction was later confirmed in 1965 when Arno Penzias and Robert Wilson detected a persistent microwave signal that seemed to come from every direction in the sky. They were not originally trying to discover the ancient glow of the universe. They were working with a sensitive radio antenna and trying to understand an unwanted background noise. After ruling out many possible sources, including famously cleaning away pigeon droppings from the antenna, the signal remained. The universe, it turned out, had been whispering into the instrument the whole time. The cosmic microwave background gave powerful evidence that the universe truly had a hot, dense past. Its existence fit beautifully with the idea of recombination and photon decoupling. The early universe had been opaque because free electrons scattered light. Then the universe cooled, neutral atoms formed, and photons began to travel freely. Billions of years later, those photons arrive as microwaves from every direction, carrying a thermal imprint of the young cosmos. This is why the universe becoming transparent matters so much to the question of temperature. It gave the universe a visible thermal relic. Before recombination, light and matter were tightly linked in a hot plasma. After decoupling, light travelled onward, preserving a record of that earlier temperature even as expansion cooled it. The CMB is not just background noise, it is an ancient message written in radiation. In a very real sense, the dark sky became possible when the universe cooled enough to let light go. Transparency was born from temperature falling. Neutral atoms formed because the universe was no longer too hot for electrons to remain bound. Light escaped the fog because the charged particles that once scattered it had settled into atoms. The universe became see-through, and the oldest observable glow began its long journey across expanding space. Everywhere in the sky, that glow remains. It is faint now, cold now, stretched into microwaves by cosmic time. But it began as light released from a universe that had just become transparent. The clear space between stars, the darkness that looks so empty, carries this memory in every direction. The universe has a temperature today partly because long ago it cooled enough to let its first light travel free. The cosmic microwave background, known as the CMB, is one of the quietest and most important things ever discovered. It is not a star, not a galaxy, and not a cloud of glowing gas. It is the cooled remnant light from the early hot universe, spread across the sky in every direction. Wherever a radio telescope looks, beyond the nearer noise of planets, stars, dust, and galaxies, there is this faint microwave glow. It is almost perfectly uniform, astonishingly old, and deeply calm, which is impressive for something that began in a universe that was essentially a glowing cosmic furnace. The CMB is often described as the afterglow of the Big Bang, though more precisely it is the light released when the universe became transparent roughly 380,000 years after the Big Bang. Before then, space was filled with hot plasma. Free electrons scattered photons again and again, preventing light from travelling freely. Once the universe cooled enough for electrons to join atomic nuclei and form neutral atoms, those photons were released. They began moving across space, and many of them are still travelling now. At the moment this light was released, the universe was much hotter than it is today. The radiation had a temperature of about 3,000 Kelvin, warm enough to glow. But the universe has expanded enormously since then, As space expanded, the wavelengths of those photons were stretched. Shorter, more energetic light became longer, less energetic light. Over billions of years, that ancient glow was stretched into microwave wavelengths. Today, this CMB has a temperature of about 2.7 Kelvin, only a little above absolute zero. That temperature is one of the great fingerprints of the universe's past. It tells us that the universe was once hot and dense, and that it has cooled as it expanded. The CMB is not a guess, a decorative theory, or a cosmic mood lighting system, although it is doing rather well at filling the universe very evenly. It is measurable radiation, detected with instruments, studied in detail, and matched closely to predictions from Big Bang cosmology. Its discovery came in 1965 through Arno Penzias and Robert Wilson at Bell Labs in New Jersey. They were using a sensitive horn antenna built for radio communication experiments, but they kept finding a persistent background signal. It seemed to come from every direction. It didn't disappear when they checked the equipment. It was not explained by nearby cities, the Milky Way, the ground, or the atmosphere. They even cleaned pigeon droppings from the antenna, a reminder that even the grandest discoveries in cosmology sometimes involve very unglamorous maintenance. At around the same time, a group at Princeton University was preparing to search for exactly such a signal. Robert Dicke, Jim Peebles, Peter Roll, and David Wilkinson understood that if the universe had once been hot and dense, there should be a cooled background of radiation left behind. Earlier theoretical work by Ralph Alpher, Robert Herman, and George Gamow had already pointed toward this relic radiation. When Penzias and Wilson's unexplained microwave signal became known, the connection was quickly recognized. What had seemed like an annoying hiss in an antenna was actually ancient light from the early universe. This discovery became one of the strongest direct pieces of evidence for the universe's thermal history. A universe that had always existed in a cold, steady state would not naturally produce this kind of all-sky blackbody radiation, but a universe that began hot and dense, then expanded and cooled, would. The CMB fits that story with remarkable precision. Its spectrum is extremely close to that of a perfect blackbody, meaning it has the pattern expected from radiation once in thermal equilibrium with matter. One of the most striking features of the CMB is how nearly the same it is in every direction. Whether a telescope looks toward one side of the sky or the opposite side, the background temperature is almost identical. This tells us that the early universe was extremely smooth on large scales. Matter and radiation were distributed very evenly, far more evenly than the modern universe, which is now filled with galaxies, clusters, voids, and enormous cosmic structures. But almost the same is not the same as perfectly the same. The CMB contains tiny temperature variations, extremely small differences from one region of the sky to another. These variations are only about 1 part in 100,000. In everyday terms, that is a whisper of a difference. In cosmology, it is treasure map. The slightly warmer and cooler patches show tiny differences in density and energy in the early universe. Over immense time, gravity amplified those tiny differences. Regions with slightly more matter attracted more matter. Slowly the seeds grew into galaxies, galaxy clusters, and the large-scale structure of the cosmos. This is why the CMB is so valuable. It is not only evidence that the universe was once hot, it is also a record of the early conditions from which later structure emerged. It shows both smoothness and slight imperfection. If the universe had been perfectly smooth, there would have been no seeds for galaxies. If it had been wildly uneven, the cosmos would look very different from what we observe. Instead, it was almost uniform, with just enough variation for gravity to begin its long, patient work. The CMB also gives the phrase "the temperature of the universe" a clear physical meaning. The universe does not have one ordinary temperature in the way a room does. Stars are hot, planets vary, gas clouds differ, and empty-looking space can mean different things depending on what is being measured. But the CMB provides a background radiation temperature that fills the observable universe. It is a thermal remnant, a cooled glow from the first time light could travel freely across space. So when modern cosmology says the universe has a temperature, the CMB is central to that statement. It is the measurable afterglow of the early universe, cooled by expansion and preserved in microwave light. It tells us that space is not simply a silent emptiness, but a place carrying ancient radiation from a hotter beginning. Even in the dark between galaxies, where matter is thin and starlight is faint, this background remains. The CMB is like a fossil made of light, though unlike a fossil in rock, it arrives from every direction at once. It is a photograph of no single object, but of the universe when it first became transparent. Its temperature is low now, but its meaning is enormous. It is the old warmth of the cosmos stretched almost to stillness, still present as a faint microwave whisper across the sky. Once the cosmic microwave background had been discovered, the next task was to listen more carefully. At first, the CMB appeared as a faint microwave glow coming from every direction in the sky, almost perfectly even, like a quiet thermal mist spread across the universe. But almost is one of the most important words in cosmology. If the early universe had been perfectly smooth, there would have been no slightly denser places for gravity to gather matter, no galaxies, no clusters, no long filaments of cosmic structure, no Milky Way, no Earth, no sleepy person wondering why the universe has a temperature. The challenge was that the differences in the CMB were incredibly small. The background radiation has an average temperature of about 2.7 Kelvin, but the tiny variations across the sky are only fractions of a Kelvin, far smaller than anything ordinary experience can make intuitive. These temperature variations are called anisotropies. Anisotropy simply means that something is not exactly the same in every direction. In the CMB, the anisotropies are tiny warmer and cooler patches, showing minute differences in the early universe's density and temperature. To measure them properly, scientists needed instruments above much of Earth's atmosphere. The atmosphere is warm, moving and full of microwave interference, which is inconvenient when trying to study a faint cosmic signal from nearly the beginning of visible time. It is a little like trying to hear a whisper from across a valley while standing next to a kettle, a washing machine, and someone opening a packet of crisps with unnecessary confidence. Spacecraft could do better. They could observe the microwave sky with less interference, greater stability, and far more precision. One of the great missions was the NASA Cosmic Background Explorer, known as COBE. Launched in 1989, COBE was designed to study the cosmic microwave background from space. One of its major achievements was confirming that the CMB has an almost perfect blackbody spectrum. This was a crucial result. A blackbody spectrum is the characteristic pattern of thermal radiation from something in equilibrium at a particular temperature. The CMB matched this pattern with extraordinary precision, showing that it truly was the cool thermal radiation from the hot early universe. That confirmation mattered because it strengthened the Big Bang model enormously. A random microwave haze would not be enough. A faint signal from local sources would not be enough. But an all-sky radiation field with an almost perfect blackbody spectrum, cooled to about 2.7 Kelvin, is exactly what would be expected if the universe had once been hot, dense, and filled with matter and radiation in thermal equilibrium. COBE showed that the universe's afterglow had the right thermal fingerprint. Kobe also detected large-scale temperature variations in the CMB. These differences were extremely small, but their discovery was profound. They showed that the early universe was not perfectly uniform. It had slight unevenness, the first measurable hints of the structure that would later grow into galaxies and galaxy clusters. The patterns were faint, but gravity is patient. Give gravity enough time, and even very small differences can become enormous. Later came the NASA Wilkinson Microwave Anisotropy Probe, known as WMAP. Launched in 2001, WMAP mapped the CMB with much greater detail than COBE. It measured the tiny temperature variations across the whole sky and helped refine estimates of the universe's age, composition, geometry, and expansion history. With WMAP, the afterglow became less like a faint blur and more like a detailed cosmic map. Not a map of planets or stars, but a map of temperature differences from when the universe was still very young. The WMAP results helped establish what is often called the Standard Model of Cosmology, usually known as the Lambda Cold Dark Matter Model. Lambda refers to dark energy, the component associated with the accelerated expansion of the universe. Cold dark matter refers to unseen matter that moves relatively slowly compared with light and helps structure form through gravity. The tiny patterns in the CMB gave scientists a way to test this model, because the shape and size of the anisotropies reveal information about what the universe contained and how it behaved. Then the European Space Agency launched the Planck spacecraft in 2009. Planck measured the CMB with even greater precision, producing the most detailed full-sky maps of its temperature variations to date. The Planck maps showed the early universe in extraordinary detail, revealing tiny differences in temperature that had been stretched across the sky by cosmic history. These maps are sometimes shown as colourful ovals with warmer and cooler regions spread across them. The colours are not what human eyes would see directly. They're enhanced to show differences so small that the real sky would look almost perfectly uniform. Those small variations are the key. In the early universe, slightly denser regions had slightly stronger gravity. They pulled in more matter. Over time, this created a feedback effect. More matter meant more gravity, and more gravity attracted still more matter. The process was slow, especially by human standards, but over hundreds of millions and then billions of years, the tiny seeds visible in the CMB grew into the cosmic web. Galaxies, clusters, filaments, and vast empty-looking voids. This means the temperature map of the early universe is also a map of future structure. The CMB does not show galaxies directly, because it comes from a time before galaxies existed. But it shows the conditions that made galaxies possible. Those faint warmer and cooler patches are like the first soft wrinkles in an otherwise smooth cosmic fabric. Later, gravity deepened them into the rich structure seen in the universe today. The temperature anisotropies also reveal sound waves in the early universe. Before recombination, matter and radiation were tightly coupled in a hot plasma. Density waves moved through that plasma, shaped by the struggle between gravity pulling matter inward and radiation pressure pushing outward. These are called baryon acoustic oscillations. The word baryon refers to ordinary matter such as protons and neutrons, and acoustic here means pressure waves, not sound in the everyday air and ears sense. There were no ears in the early universe, which is probably just as well, because the cosmos had other priorities. The patterns left by those ancient waves appear in the CMB temperature variations. By studying them, scientists can learn about the amount of ordinary matter, and dark energy in the universe. The afterglow is not only beautiful, it is precise. It allows cosmology to become a measured science rather than a collection of grand guesses. Mapping the CMB transformed a faint microwave signal into one of the most detailed records of the young universe. COBE confirmed the thermal blackbody glow. WMAP sharpened the picture of tiny temperature differences. Planck refined it further, giving scientists an exceptionally detailed view of the early cosmic pattern. Each mission made the universe's afterglow clearer, as though an ancient photograph were being gently brought into focus, and what the maps reveal is deeply connected to why the universe has a temperature. The CMB is not merely a cold background, it is a thermal record. Its average temperature tells the story of expansion and cooling. Its tiny variations tell the story of structure beginning to form. The largest galaxy clusters in the modern universe, with their hot gas, dark matter, and thousands of galaxies, began from very slight differences in density and temperature long before any star had shone. So the universe's faint microwave glow is not smooth emptiness. It is the earliest visible texture of everything that followed. It is the cooled afterglow of a hot beginning, mapped across the sky in tiny variations, each one a quiet clue. From those delicate differences came galaxies, clusters, stars, planets, and eventually minds capable of measuring the afterglow and wondering softly why the universe was warm in the first place. Empty space has a wonderfully misleading name. It sounds clean, simple, and final, as though between the galaxies there is just nothing at all. No matter, no light, no warmth, no memory. A perfect blank. But in physics, empty space is rarely truly empty. It can be emptier than anything naturally found on Earth, and still contain more than enough to keep scientists busy for a very long time, which is exactly the sort of thing scientists tend to appreciate. Intergalactic space is extraordinarily sparse. Compared with the air in a room, it is almost unimaginably empty. A single breath contains vast numbers of molecules, all colliding, bouncing, and carrying heat. Between galaxies, matter may be spread so thinly that only a few particles occupy a volume that, on Earth, would be packed with air. But sparse is not the same as nothing. Space contains photons, including the cosmic microwave background. It contains neutrinos, ghostly particles that pass through ordinary matter with almost no interaction. It contains dark matter, known through its gravitational effects. It contains magnetic fields, cosmic rays, and extremely thin gas stretched across enormous distances. This is why the phrase "the temperature of space" can be tricky. It sounds as if space should have one neat temperature, like a freezer, a room, or an oven. But empty-looking space does not behave like air in a kitchen. Temperature can mean different things depending on what is being measured. The radiation in space can have a temperature. Sparse particles in a gas can have a temperature. An object placed in space can reach its own temperature, depending on how much energy it absorbs and how much it radiates away. These are related ideas, but they are not identical. The cosmic microwave background, for example, has a temperature of about 2.7 Kelvin. That is the temperature associated with the ancient radiation filling the universe. It is not the same as saying that every object in deep space immediately becomes 2.7 Kelvin. An object's temperature depends on its surroundings, its surface, its ability to absorb and emit radiation, and whether it is exposed to sunlight or shielded from it. Temperature is always a relationship between energy and matter, or energy and radiation, not simply a label stamped onto a location. Near Earth, this becomes very practical. An astronaut or spacecraft in sunlight can become hot, because sunlight carries energy. Without an atmosphere to scatter and soften that radiation, in the same familiar way as on Earth's surface, direct sunlight in space can heat exposed surfaces strongly. Meanwhile, a surface in shadow can become extremely cold, because it is no longer absorbing sunlight, but can still radiate its own heat away into space. The same spacecraft can have a hot sunlit side and a very cold shadowed side at the same time. Space is quite happy to be dramatic about temperature gradients. On Earth, heat usually moves by conduction, convection, and radiation. Conduction happens when heat passes through direct contact, such as a spoon warming in a cup of tea. Convection happens when moving fluids carry heat, as warm air rises or boiling water circulates. Radiation happens when energy travels as electromagnetic waves, such as infrared light leaving a warm object. In a vacuum, conduction and convection become weak or absent because they need matter. There are too few particles to carry heat efficiently through contact or flowing motion. Radiation becomes the main way objects gain and lose heat. This is why space can be dangerous in a way that is different from ordinary cold air. A freezing wind removes heat from the body by moving cold air across skin. In space, there is no thick air to blow heat away. Instead, an object cools mostly by radiating infrared energy. If it is receiving sunlight, it may heat up. If it is shielded from the sun and other strong sources, it may cool dramatically. Space itself is not cold like a cold bath. It is cold like a vast place where there may be very little matter to share heat with, and where radiation decides most of the thermal story. The thin matter that does exist between galaxies is called the intergalactic medium. It is made mostly of sparse gas, much of it hydrogen and helium, spread through the space between galaxies. Some of this gas is relatively cool by cosmic standards, while some is extremely hot. In particular, scientists study the warm-hot intergalactic medium, a diffuse form of gas that may reach temperatures from hundreds of thousands to millions of Kelvin. That sounds fiercely hot, and in terms of particle energy it is, but the gas is so thin that it would not feel hot in the ordinary sense. There are simply not enough particles hitting an object to transfer heat the way dense hot air or water would. This difference between temperature and heat content is important. A tiny spark can have a high temperature, but it does not contain enough total energy to warm a room. A bathtub of warm water has a lower temperature than a flame, but far more thermal energy overall because it contains much more matter. In intergalactic space, individual particles can be moving very fast, giving the gas a high temperature, while the overall density is so low that its heating effect on a solid object would be weak. Cosmic temperature often asks not just how energetic particles are, but how many of them are present. Photons add another layer. The universe is filled with a cosmic microwave background, but also with starlight, infrared radiation from dust, X-rays from hot gas, and high-energy gamma rays from violent events. Cosmic rays, which are energetic particles rather than rays of light, also move through space. Neutrinos stream through the cosmos almost unnoticed. Magnetic fields thread through galaxies and clusters. Dark matter shapes structure through gravity, even though it doesn't appear to interact with light in the usual way. Empty space is not crowded in the everyday sense, but it is physically rich. So the temperature of space is not one simple value. If the subject is the cosmic microwave background, the answer is about 2.7 Kelvin. If the subject is thin gas between galaxies, the temperature may be far higher. If the subject is a spacecraft, the answer depends on sunlight, shadow, surface materials, orientation, and how well it radiates heat. If the subject is a region inside a galaxy cluster, the surrounding plasma may be millions of Kelvin. If the subject is a dark, shielded object far from stars, it may slowly cool toward the background radiation around it. This is why empty space is such a useful illusion. It is empty enough to seem silent, dark and still. But it is not empty enough to be nothing. It contains faint light from the early universe, rare particles moving across unimaginable distances, diffuse gas shaped by gravity, and radiation from stars and galaxies. Its temperatures are not simple because its contents are not simple. The universe has a temperature not because space is one enormous room with one setting, but because even the emptiest regions participate in the movement and exchange of energy. Radiation fills space, particles drift through it, objects absorb and emit light. Ancient microwaves carry the cooled memory of the early cosmos. The dark between galaxies is sparse, but it is not blank. It is a quiet physical environment, and temperature is one of the ways its hidden contents reveal themselves. Stars are the great furnaces of the universe, though they are not furnaces in the ordinary sense. They are not burning like wood in a fireplace or coal in an old engine. Ordinary burning is a chemical reaction, where atoms rearrange their bonds and release energy. A star is doing something far deeper. In its core, under immense pressure and temperature, atomic nuclei are being transformed. Matter is not merely changing partners in a chemical dance, it is changing its nuclear identity. The source of a star's heat and light is nuclear fusion. Fusion happens when light atomic nuclei combine to form heavier nuclei. In stars like the Sun, the main fuel is hydrogen, the simplest and most abundant element in the universe. Deep in the core, hydrogen nuclei are pushed close enough together for nuclear reactions to occur. They eventually form helium, and in the process, energy is released. This energy begins as motion and radiation inside the star, then slowly works its way outward until it escapes as the light and warmth that can cross space. The reason fusion releases energy is connected to nuclear binding energy. Atomic nuclei are held together by the strong nuclear force, one of the fundamental forces of nature. Some arrangements of protons and neutrons are more tightly bound than others. When lighter nuclei combine into a more tightly bound nucleus, a small amount of mass is converted into energy. This is described by Albert Einstein's famous mass-energy relation, which can be written in words as energy equals mass multiplied by the speed of light squared. In a star, that tiny conversion of mass into energy happens on an enormous scale. For a long time, the source of starlight was a mystery. Chemical burning could not power the sun for billions of years. Gravitational contraction could keep a star shining for a while, but not nearly long enough to match the age of Earth and the solar system. In the early 20th century, Arthur Eddington suggested that stars might be powered by the transformation of hydrogen into helium. It was a bold and elegant idea, pointing toward the nuclear heart of stellar energy, before all the details were fully known. Later, Hans Bethe explained the main fusion pathways that power stars. In stars like the Sun, the proton-proton chain is the dominant process, gradually converting hydrogen into helium through a series of nuclear reactions. In more massive stars, the carbon-nitrogen-oxygen cycle becomes more important, using carbon, nitrogen and oxygen nuclei as stepping stones in the fusion of hydrogen into helium. These processes revealed that stars are not simply hot objects in space. They are vast nuclear engines, held together by gravity and lit from within by fusion. The temperatures involved are immense. The visible surface of the Sun, called the photosphere, is about 5,700 Kelvin. That is hot enough to make the Sun shine mostly in visible light, with plenty of infrared and ultraviolet radiation as well. But the surface is cool compared with the core. At the centre of the Sun, the temperature is roughly 15 million Kelvin. There, pressure is so enormous that hydrogen nuclei can overcome their mutual electric repulsion, often enough for fusion to occur. The core is where the Sun's long patient becomes light. Different stars have different surface temperatures, and those temperatures help determine their colours. Cooler stars glow red or orange. They emit more of their visible light toward the redder end of the spectrum. Hotter stars can appear white or blue-white, because their radiation is shifted toward shorter wavelengths. Blue stars are not blue because they're chilly, as with taps and weather maps. In astronomy, blue usually means hotter, which is one of the universe's little jokes at the expense of bathroom plumbing. The sun sits in a middle range. From space, it appears essentially white, because it emits light across the visible spectrum. From Earth's surface, it can look yellow, orange, or red when its light passes through more atmosphere, especially near sunrise or sunset. That change is caused by scattering in Earth's air, not by the sun suddenly changing mood at the horizon. Its surface temperature remains about 5,700 Kelvin, while its light is filtered and softened by the atmosphere. Stellar colour gives astronomers a way to estimate temperature. A star's spectrum, the detailed spread of light across wavelengths, reveals even more. By studying spectra, scientists can determine not only surface temperature, but also chemical composition, motion, rotation, magnetic fields, and other properties. The light from a star is a message written in radiation. Its colour is the broad hint. Its spectrum is the detailed handwriting. Stars also show why the universe can be cooling overall while still containing regions of intense heat. On the larger scale, the cosmic microwave background has cooled as space has expanded. Its ancient radiation has been stretched down to about 2.7 Kelvin, yet inside galaxies gravity gathers gas and dust into dense regions. When enough mass collects, the pressure and temperature at the centre can rise until fusion begins. A star is born, and a new local source of heat and light appears inside an expanding, cooling universe. This is not a contradiction. The universe is not cooling in the sense that every place becomes colder at the same rate. Cosmic cooling refers especially to the background radiation and the large-scale expansion of space. Local physics can still concentrate energy. Gravity can pull matter together. Compression can heat gas. Fusion can release nuclear energy stored in atomic nuclei. Supernovae can blast heat into space. Accretion disks around compact objects can become fiercely hot. The universe is thermally uneven, full of local fires inside a broader cooling history. Stars are among the most important of those local fires. They heat surrounding dust. They ionize gas. They shape nebulae with radiation and stellar winds. They forge heavier elements in their interiors and in their depths. The carbon in living tissue, the oxygen in water, the iron in blood, and many other elements were made through stellar processes across cosmic time. In that sense, stars do not merely warm the universe, they chemically enrich it. They turn simple matter into the ingredients for planets, oceans, atmospheres, and living cells that may one day complain about the weather. The sun is the nearest example of this grand process. Its light takes a little over 8 minutes to reach Earth. By the time sunlight falls on a leaf, warms a stone, drives weather, or glows through closed curtains in the morning, it has travelled from a nuclear furnace 93 million miles away. That warmth began in the core as fusion energy, spent a very long time moving outward through the sun's interior, then crossed space as radiation. So stars are central to the universe's temperature story. They prove that heat is not only a fading relic from the Big Bang. New heat can be generated where gravity gathers matter and nuclear fusion begins. The cosmos may be expanding and its ancient background glow may be cooling, but stars keep lighting local regions from within. They're islands of fierce temperature in a darkening sea, turning gravity and nuclear physics into light. The universe has a temperature partly because it has a past, but also because it has engines. Stars are those engines at their most familiar and beautiful. They burn without burning, shine without flame, and warm worlds across distances that the mind can barely hold. In their cores, matter is pressed into transformation. In their light, the cold between worlds is briefly interrupted. A planet's temperature is never decided by one thing alone. It is a balance, a quiet negotiation between energy arriving, energy leaving, and all the complicated ways a world handles the light that falls upon it. A planet receives radiation from its star. Some of that light is reflected back into space by clouds, ice, dust, oceans, or pale rock. Some is absorbed by the surface and atmosphere, warming the planet. Then the planet gives energy back by emitting infrared radiation, a form of light human eyes cannot see but warm objects naturally release. This balance is why planetary temperature is not simply a matter of distance from a star. Distance matters enormously, of course. A world closer to the sun receives more intense sunlight than one farther away. But distance is only the beginning. Atmosphere, rotation, clouds, oceans, surface colour, volcanic activity, ice cover, and the chemistry of gases all help decide whether a planet keeps warmth, loses it quickly, or traps it with slightly too much enthusiasm, like a blanket that has forgotten when to stop. The greenhouse effect is one of the most important parts of this story. It is a real physical process, not a metaphor invented for climate charts. Sunlight reaches a planet, and some of it warms the surface. The warmed surface then emits infrared radiation upward. Certain gases in the atmosphere absorb some of that infrared radiation and re-emit it in different directions, including back toward the surface. Water vapour, carbon dioxide, methane and ozone are important greenhouse gases. They do not create energy from nothing. They slow the escape of heat to space, changing the planet's final temperature. Earth depends on this natural greenhouse effect. Without it, the planet would be much colder. Earth's effective temperature, the temperature it would have if it simply balanced absorbed sunlight with emitted radiation without the warming effect of the atmosphere, is roughly 255 Kelvin. That is well below the freezing point of water. Earth's actual average surface temperature is closer to 288 Kelvin, though it varies greatly from place to place and season to season. The difference is largely due to the natural greenhouse effect, along with clouds, oceans, and atmospheric circulation. In other words, Earth is not warm merely because it is the right distance from the sun. It is warm because it is the right distance with the right kind of atmosphere, oceans, rotation, and surface conditions. The planet is less a simple rock and more a very complicated thermal committee. Venus shows how powerful an atmosphere can be. Venus is closer to the sun than Earth, but its extreme heat is not only because of distance. It has a thick carbon dioxide atmosphere and clouds of sulfuric acid, creating an intense greenhouse effect. Its surface temperature is around 735 Kelvin, hot enough to melt lead. Venus is often called Earth's sister planet because of its similar size, but thermally speaking it is more like the sibling who moved into a greenhouse and welded the windows shut. Mars gives the opposite lesson. Mars is farther from the Sun, and it has a very thin atmosphere, mostly carbon dioxide but far too sparse to trap much heat. Its average surface temperature is around 210 Kelvin, though it changes widely between day and night, equator and pole, surface and atmosphere. Mars shows that having greenhouse gases is not enough by itself. The atmosphere must also be thick enough, and the planet must receive enough sunlight for those gases to have a strong warming effect. The Moon shows another version of the same principle. It is nearly the same distance from the Sun as Earth, but it has no substantial atmosphere. Without air to move heat around, and without oceans or clouds to soften temperature extremes, its surface changes dramatically between sunlight and shadow. During the lunar day, sunlit regions can become extremely hot. During the long lunar night, the surface can plunge into intense cold. Distance from the Sun has barely changed compared with Earth, But the thermal behavior is completely different because the Moon lacks the atmospheric blanket and fluid systems that redistribute energy. This is why organizations such as NASA, the National Oceanic and Atmospheric Administration, and the Intergovernmental Panel on Climate Change study planetary atmospheres, radiation, clouds, oceans, and surface temperatures so carefully. Temperature is not just a number on a thermometer. It is the result of energy moving through a system. On Earth, climate science examines how sunlight enters, how much is reflected, how infrared radiation escapes, how greenhouse gases affect that escape, and how oceans and air currents transport heat around the globe. Planetary warmth also depends on albedo, the fraction of incoming light a world reflects. Ice and bright clouds reflect a lot of sunlight. Dark rock, ocean water, and vegetation tend to absorb more. A higher albedo can cool a planet by sending more sunlight away. A lower albedo can warm it by allowing more energy in. This matters across the solar system. Bright icy moons reflect sunlight efficiently, while darker surfaces absorb more. A planet's colour, chemistry, and cloud cover become part of its thermal personality. Rotation matters too. A quickly rotating planet can spread heating between day and night more effectively if it has an atmosphere or oceans to help. A slowly rotating world may develop larger temperature contrasts. Oceans are especially important on Earth because water stores heat well and moves it through currents. The ocean does not just sit there looking scenic. It acts as a giant heat reservoir, which is more impressive than it sounds, and slightly less relaxing if imagined as a global bathtub with weather attached. So planetary temperature is relational. It depends on a star's energy, a planet's distance, its reflectivity, its atmosphere, its surface, its rotation, and its ability to absorb, move, trap, and release radiation. No world is warm or cold in isolation. Each one is part of an energy conversation with space. This brings the cosmic temperature story closer to home. The universe contains ancient background radiation, hot stars, cold shadows, thin gas, and glowing plasma. But planets show how temperature becomes local and specific. A world is not merely placed in the universe like a stone in a dark room. It responds, it reflects, absorbs, radiates, circulates, and sometimes keeps just enough warmth for oceans, clouds, and life to exist beneath a sky. Cold in the solar system is not always found where expected. It is tempting to imagine temperature as a simple matter of distance from the sun, with worlds becoming colder in a neat outward sequence, like a cosmic freezer with shelves. In broad terms, that is partly true. The farther a world is from the sun, the less sunlight it receives. But the solar system is not quite so tidy. Some of its coldest places are not only far away, they're hidden in shadow, protected from sunlight, or shaped by surfaces and atmospheres that handle heat in unusual ways. On worlds with little or no atmosphere, temperature can change dramatically between sunlight and darkness. An atmosphere helps move heat around by winds, pressure, and circulating gases. Without it, there is very little conduction or convection to spread warmth from one place to another. Surfaces mostly gain energy by absorbing sunlight and lose energy by radiating infrared light back into space. This means a sunlit rock can become intensely warm, while a nearby shadow can remain bitterly cold. The difference may be separated by only a ridge, a crater wall, or a patch of ground where sunlight simply never arrives. The Moon offers a beautiful example. Most of the lunar surface experiences huge temperature swings between day and night, because the Moon has no substantial atmosphere to soften the extremes. But near its poles, some crater floors lie in permanent shadow. Because the Moon's axis is only slightly tilted, sunlight never climbs high enough to reach the deepest parts of these craters. These permanently shadowed regions can remain extremely cold for millions or even billions of years. They are sometimes cold enough to preserve water ice and other volatile compounds, like natural freezers built not by machinery, but by geometry. Mercury has a similar surprise. It is the closest planet to the Sun, so it sounds like a place where cold should have packed its bags and left. Its sunlit surface can become fiercely hot, but near Mercury's poles, deep craters can also contain permanent shadows. Radar observations and spacecraft data from NASA's Messenger mission have supported the presence of ice in some of these polar cold traps. A planet close enough to be scorched by sunlight can still hide ancient frost in places the sun never reaches. Temperature, once again, has a talent for being less obvious than expected. Farther out, the cold becomes more widespread. Comets spend much of their lives in the outer solar system or beyond the orbit of Neptune, preserving ices of water, carbon dioxide, carbon monoxide, methane, and other compounds. When a comet moves closer to the Sun, some of those ices turn directly into gas through sublimation, releasing dust and forming a glowing coma and tail. A comet is not just a dirty snowball, though that nickname is charmingly blunt. It is a preserved chemical record from the early solar system, stored for immense stretches of time in deep cold. Beyond Neptune lies the Kuiper Belt, a distant region filled with icy bodies, including Pluto and many smaller worlds. Sunlight out there is faint compared with sunlight at Earth. Pluto's surface temperature is around 40 Kelvin, though it varies with location and season. That is cold enough for nitrogen, methane, and carbon monoxide to exist as ices on its surface. Yet Pluto is not a dead frozen pebble. NASA's New Horizons spacecraft revealed mountains of water ice, plains of nitrogen ice, possible cryovolcanic features, and a surprisingly complex surface. Cold did not erase Pluto's personality. It simply gave it stranger materials to work with. Triton, Neptune's largest moon, is another frozen world with activity. It has a surface rich in nitrogen ice and an extremely thin atmosphere. Voyager 2 observed dark geyser-like plumes, likely driven by sunlight warming subsurface nitrogen and causing it to erupt through the surface. Triton is intensely cold, but still capable of change. At these temperatures, substances that are gases on Earth can behave like rock, frost, or flowing ice. The ordinary categories of solid, liquid, and gas begin to feel wonderfully local and Earth-biased. Europa and Enceladus show that surface cold can hide internal warmth. Europa, a moon of Jupiter, is covered by an icy shell, but evidence strongly suggests a global ocean beneath it. Enceladus, a small moon of Saturn, sprays water vapour and icy particles from fractures near its south pole. The Cassini spacecraft detected these plumes, revealing salts and organic molecules among the ejected material. Both moons are far from strong sunlight, and their surfaces are extremely cold, yet their interiors can be warmed by tidal heating. Tidal heating happens when gravity stretches and flexes a world as it orbits a larger planet, especially if the orbit is slightly elliptical or influenced by other moons. This flexing creates internal friction, turning orbital and gravitational energy into heat. Europa is pulled by Jupiter and affected by neighbouring moons. Enceladus is flexed by Saturn's gravity. The result is that internal oceans and geological activity can persist beneath frozen crusts. Cold, in these cases, is only the surface story. Titan, Saturn's largest moon, adds another strange version of cold complexity. Its surface temperature is about 94 Kelvin, cold enough that water ice behaves almost like rock. Yet Titan has a thick nitrogen-rich atmosphere, clouds, rain, lakes, and seas of liquid methane and ethane. The Cassini-Huygens mission showed Titan to be one of the most chemically fascinating worlds in the solar system. It is deeply cold, but not simple. It has weather, landscapes, dunes, and liquid cycles, just built from materials that on Earth would usually be gases. These cold worlds show that temperature depends on more than distance from a star. Sunlight matters, but so do shadow, atmosphere, surface reflectivity, rotation, internal heat, and chemistry. A crater near the Sun can preserve ice. A moon far from the Sun can hide a warm ocean. A frozen dwarf planet can reshape its surface. A cold atmosphere can produce methane rain. The solar system is full of thermal exceptions, each one quietly reminding us that temperature is not a single ruler laid across space. Cold is not the same as stillness. It can preserve, conceal, slow, and transform. In frozen shadows and distant worlds, energy still moves, just in subtler ways. The universe does not need warmth everywhere to remain active. Sometimes its most interesting stories unfold under ice, in darkness, where the sun is faint and the heat comes from deep within. Some of the hottest ordinary matter in the modern universe is not hidden inside stars. It is not packed into glowing stellar cores, or sealed beneath the surfaces of planets, or blazing in the familiar shapes of suns. A great deal of it is spread through the enormous spaces between galaxies, especially inside galaxy clusters, where gravity has gathered hundreds or thousands of galaxies into vast cosmic cities. Between those galaxies lies an extremely thin, extremely hot plasma called the intracluster medium. At first, this sounds almost backwards. The space between galaxies looks dark and empty. It seems like exactly the wrong place to find matter at tens of millions of Kelvin. But galaxy clusters are not just collections of galaxies. They are enormous gravitational structures filled with dark matter, galaxies, hot gas, magnetic fields, and radiation. In many clusters, the hot gas between the galaxies contains more ordinary matter than the galaxies themselves. The stars may be brighter and easier to imagine, but the thin plasma around them is a major part of the cluster's mass in normal matter. The intracluster medium is made mostly of ionized hydrogen and helium, along with traces of heavier elements produced by earlier generations of stars and supernovae. Ionosed means the atoms have been stripped of electrons, creating a plasma of charged particles. This gas can reach temperatures of 10 million, 50 million, or even more than 100 million Kelvin in the most massive clusters. At those temperatures, the gas emits X-rays, a high-energy form of light that cannot be seen by human eyes but can be detected by specialized observatories. This is where space telescopes become essential. Earth's atmosphere blocks most X-rays from space, which is excellent for living things and slightly inconvenient for X-ray astronomy. To study the hot gas in galaxy clusters, scientists use observatories above the atmosphere. The Chandra X-ray Observatory, launched by NASA in 1999, has produced detailed views of hot cluster gas, shockwaves, cavities, and collisions between galaxy clusters. XMM Newton, operated by the European Space Agency, has also played a major role in measuring X-ray emission from the intracluster medium. These observatories allow astronomers to map gas so hot that it shines in radiation. Human eyes were never built to see. The heating comes largely from gravity. A galaxy cluster has an enormous gravitational well, shaped mostly by dark matter, along with galaxies and gas. As gas falls into this deep gravitational well, it accelerates. Its gravitational potential energy turns into motion. Then, as streams of gas collide, compress, and pass through shocks, much of that motion becomes thermal energy. The particles move faster in random directions, and the gas temperature rises. Gravity in this setting behaves like a vast heating engine, It pulls matter inward, and the falling matter converts its motion into heat. This is one reason the universe can contain very hot regions, even while the cosmic microwave background has cooled to about 2.7 Kelvin. On the larger scale, the background radiation of the universe is becoming colder as space expands. But gravity does not simply let everything fade evenly. It gathers matter. It builds stars, galaxies, clusters, and filaments. Wherever matter falls into deep gravitational wells, energy can become concentrated again. The universe cools overall in one sense, while local structures heat up dramatically in another. The intracluster medium also helps reveal the difference between temperature and heat content. Temperature tells us about the average energy of particles. Heat content depends not only on temperature, but also on how much matter is present. A gas can have a very high temperature because its particles are moving extremely fast, yet still be so thin that each small volume contains very few particles. This is why the hot gas between galaxies would not feel hot in the familiar way that steam or fire feels hot. There are not enough particles in an ordinary human-sized volume to transfer energy quickly to an object placed there. A spark can be very hot but contain little total energy. A warm bath is cooler than a flame but contains much more thermal energy because there is far more matter involved. The intracluster medium is similar in spirit, though on a scale that makes bathtubs seem deeply unambitious. Its particles can be tremendously energetic, giving the gas a temperature of millions of Kelvin, but the gas is extraordinarily diffuse. Across the immense volume of a galaxy cluster, however, all that thin gas adds up to a vast reservoir of thermal energy. This hot plasma is not merely sitting quietly. It responds to events within the cluster. When galaxy clusters collide, their gas can form enormous shock fronts, like cosmic bow waves. One famous example is the Bullet cluster, where observations of hot gas and gravitational mass helped provide evidence for dark matter. In many clusters, supermassive black holes in central galaxies also influence the intracluster medium. Jets from active galactic nuclei can carve cavities in the hot gas, stirring it and injecting energy. Even in the seemingly empty spaces between galaxies, the thermal environment is dynamic. The intracluster medium also carries the chemical history of stars. Elements heavier than hydrogen and helium are forged inside stars and scattered by supernovae and stellar winds. Over time, some of that enriched material leaves galaxies and mixes into the surrounding cluster gas. X-ray observations can detect signs of elements such as iron, oxygen, silicon, and sulfur. The hot gas between galaxies is therefore not only a record of gravity and temperature, it's also a record of stellar life and death spread across enormous volumes. This makes the universe's temperature story more layered. The cosmic microwave background tells us about the cooled radiation of the early universe. Stars show how fusion creates local heat and light. Planets show how atmospheres and surfaces manage energy. Cold moons and shadowed craters show how sunlight, geometry, and internal heating shape frozen worlds. But galaxy clusters show something else. Gravity itself can make ordinary matter intensely hot across spaces that look empty. So the universe is not cooling in a simple, uniform way. Its ancient background glow is cooling as space expands, but gravity continues to gather matter into structures where energy is concentrated, transformed, and released. Between galaxies, in the great clusters of the cosmos, thin plasma shines in X-rays at temperatures far beyond the surfaces of most stars. It is almost invisible to ordinary sight, but not to physics. The darkness between galaxies is not always cold. Sometimes it is filled with one of the hottest forms of ordinary matter in the universe, spread so thinly that only the most patient instruments can hear its heat. Black holes seem, at first, like the last place temperature should belong. A temperature usually suggests heat, glow, radiation, particles moving and sharing energy. A black hole, in the classical picture, is the opposite of that. It is a region of space-time where gravity is so intense that beyond a boundary, called the event horizon, nothing can escape to the outside universe, not even light. If nothing can escape, then a black hole should be perfectly dark, silent, final, a cosmic one-way door with no polite return policy. That was the older picture. In Einstein's general theory of relativity, a black hole is described by gravity and geometry. Matter collapses into a region so compact that an event horizon forms around it. Anything crossing that horizon can still move locally, but all future paths lead deeper inward. To an outside observer, the horizon marks the boundary beyond which information and light cannot return. In this classical view, black holes are not warm objects. They do not shine by themselves, they simply absorb. Then thermodynamics began to creep into the story, which is very much its style. The first major clue came from Jacob Bekenstein in the early 1970s. He considered the relationship between black holes and entropy. Entropy, in thermodynamics, is connected to how many microscopic arrangements can produce the same large-scale state. It is also tied to information and the direction of physical processes. Bekenstein argued that black holes should have entropy, and that this entropy should be related to the area of the event horizon, not the volume inside. This was a strange and powerful idea. If black holes have entropy, then they behave in some ways like thermodynamic systems. And if a system has entropy, the question of temperature begins to appear nearby, like a cat silently entering a room where it was not invited. At first, this seemed only like an analogy. Black hole mechanics had equations that resembled thermodynamics, but many physicists were unsure whether the resemblance was physically real. Stephen Hawking changed that. In 1974, Hawking used quantum field theory in curved spacetime to show that black holes should not be completely black. When quantum effects are considered near the event horizon, a black hole can emit radiation. This radiation is now called Hawking radiation. It means black holes can be assigned a genuine temperature. The idea was startling because it connected three enormous areas of physics: general relativity, quantum theory, and thermodynamics. Hawking radiation is often described using a simple image of particle pairs appearing near the horizon, with one particle falling in and the other escaping. That picture can be useful as a rough metaphor, but it should not be treated as the full explanation. The deeper idea is that quantum fields behave differently in curved space-time, and what counts as empty space for one observer does not always remain empty in the same way for another. Near a black hole horizon, this leads to radiation that can be observed from far away. The black hole loses energy through that radiation, which means it can slowly lose mass over time. The temperature of a black hole depends on its mass. Larger black holes are colder, smaller black holes are hotter. This is beautifully counterintuitive because ordinary objects often become hotter when more energy is packed into them. But black holes follow their own gravitational rules. A black hole with the mass of the Sun would have a Hawking temperature of only a tiny fraction of a Kelvin, far colder than the cosmic microwave background, which is about 2.7 Kelvin. Stellar mass black holes are colder still if they have several times the Sun's mass. Supermassive black holes, with millions or billions of solar masses, have temperatures so extraordinarily low that the numbers become almost absurdly small. This means that real astrophysical black holes today are not glowing brightly from Hawking radiation. They are colder than the background radiation of the universe. Instead of losing mass rapidly, they absorb far more energy from their surroundings than they emit through Hawking radiation. A black hole in the modern universe is more likely to be warmed by the cosmic microwave background than to noticeably warm anything else through its own quantum glow. It is the kind of object that technically has a temperature while being spectacularly unhelpful as a heater. Smaller black holes would be different. The smaller the black hole, the higher its Hawking temperature. A hypothetical, very tiny black hole would radiate much more strongly. If such a black hole became small enough, it could lose mass faster and faster as its temperature rose, potentially ending in an energetic final burst. No confirmed tiny primordial black holes have been observed, but they remain an important theoretical possibility in discussions of the early universe, dark matter, and high-energy cosmology. Black hole temperature also changes the meaning of emptiness. A black hole is not merely an object inside the universe. It is a place where space-time, energy, and information meet under extreme conditions. The event horizon behaves like a thermodynamic surface. Its area is connected to entropy. Its quantum behavior is connected to radiation. Its mass is connected to temperature. These links suggest that temperature is not only a property of gas, stars, planets, or light. It reaches into the structure of gravity itself. This is why black holes matter so much to the wider story. The universe has a temperature not only because particles move and radiation glows, but because temperature appears wherever energy, information, and physical law become linked. In black holes, that link sits at the edge of current understanding. Scientists still do not have a complete theory of quantum gravity, the deeper framework that would fully unite quantum mechanics with general relativity. Black holes are one of the places where that missing theory seems most urgently needed. So black holes are not just dark endings. They are laboratories of thought, where the universe quietly reveals that heat is stranger than fire and temperature is deeper than touch. A black hole can be colder than the background of space, yet still possess entropy and emit radiation in principle. It can trap light classically, yet glow quantum mechanically. It can seem like the most final object in nature, while quietly pointing toward unfinished physics. Temperature, then, reaches all the way to the horizon. It belongs not only to warm cups, shining stars, icy moons, and ancient microwaves, but also to the boundary around a black hole where gravity bends the rules of ordinary intuition. Even there, in one of the darkest places the universe allows, physics finds a faint thermal whisper. Some of the coldest places known are not hidden in distant space. They are not on Pluto, not inside the shadowed craters of the moon, and not drifting between galaxies where the cosmic microwave background glows at about 2.7 Kelvin. The coldest places science can study are often made deliberately, inside laboratories, by researchers who have learned how to remove almost every trace of ordinary thermal motion from small clouds of atoms. This is one of the more surprising turns in the story of temperature. Space is cold in many ways, but it is not the coldest environment humans know how to describe. In carefully controlled experiments, scientists can cool matter to temperatures only billionths of a Kelvin above absolute zero. These temperatures are far colder than the cosmic microwave background. They are colder than deep interstellar clouds, colder than the night side of distant moons, and colder than almost anywhere nature casually provides. Apparently, when humans cannot sleep, they build machines that make atoms nearly stop dancing. The purpose is not simply to win a competition against the universe, satisfying though that might sound. Ultra-cold physics allows scientists to study matter near its lowest possible thermal energy. When atoms are cooled to these extremes, their ordinary motion slows dramatically, and quantum behavior becomes easier to observe. Quantum mechanics is always present, but at everyday temperatures it is often hidden beneath thermal motion, collisions, and noise. Cooling atoms is like quieting a room until the softest sounds can finally be heard. One of the most important examples is the Bose-Einstein condensate, A Bose-Einstein condensate is an unusual state of matter formed when a gas of certain atoms is cooled to extremely low temperatures, very close to absolute zero. At that point, many atoms can enter the same quantum state and begin behaving less like separate little particles and more like one collective quantum object. The result is matter with strange properties, where quantum effects appear on a scale large enough for scientists to study directly. The idea began with Satyendra Nath Bose, an Indian physicist who developed a new way of describing particles of light in the early 20th century. Albert Einstein extended Bose's work to atoms and predicted that at extremely low temperatures certain particles could gather into the same lowest energy state. This prediction was made long before laboratory technology could reach the necessary conditions. For decades, the Bose-Einstein condensate remained a theoretical possibility, waiting patiently in the cold end of physics. The first widely recognized Bose-Einstein condensates in dilute atomic gases were created in 1995. Eric Cornell and Carl Wieman produced one using rubidium atoms, while Wolfgang Kettel soon created another using sodium atoms. These achievements opened a new field of ultra-cold atomic physics, and later earned them the Nobel Prize in Physics. What had once been a mathematical prediction became a real state of matter, visible through careful measurement, made from atoms cooled to almost unimaginable stillness. To reach these temperatures, scientists use methods such as laser cooling, magnetic trapping, and evaporative cooling. Laser cooling may sound like a contradiction, because lasers are often associated with heat, cutting, or dramatic science fiction doors that should not be opened. But lasers can be tuned so that atoms absorb and emit light in ways that slow them down. Slower atoms mean lower temperature. After that, evaporative cooling can remove the most energetic atoms from a trapped cloud, leaving the remaining atoms even colder. It is a little like cooling soup by removing only the most energetic noodles, although the comparison becomes scientifically risky quite quickly. These experiments are delicate. The ultra-cold clouds are tiny, isolated, and carefully controlled. They are not cold rooms, cold planets, or cold regions of space. They are small systems where a limited number of atoms have been cooled with extraordinary precision. That distinction matters. A laboratory Bose-Einstein condensate can be far colder than the cosmic microwave background, but it contains very little matter. It is not a large reservoir of cold. It is a finely prepared quantum system. One remarkable example is NASA's Cold Atom Laboratory aboard the International Space Station. This facility allows scientists to study ultra-cold atoms in microgravity. On Earth, gravity pulls atomic clouds downward, limiting how long some experiments can observe them freely. In orbit, microgravity gives researchers more time to examine the behavior of cold quantum gases. The International Space Station becomes, in a very literal sense, a laboratory for some of the coldest matter humans can make, floating above a planet that is mostly busy being warm, weathered, and slightly noisy. Ultra-cold atoms help scientists explore fundamental physics. Bose-Einstein condensates can be used to study superfluidity, where matter flows without ordinary viscosity. They can help simulate other quantum systems that are difficult to study directly. They can improve precision measurements and contribute to technologies such as atomic clocks, quantum sensors, and tests of basic physical principles. Temperature in this setting becomes a tool for removing distraction. The colder the atoms become, the clearer certain quantum behaviors can appear. This also gives absolute zero a deeper meaning. Scientists can approach it extremely closely, but they cannot simply reach it in a perfect final way. The third law of thermodynamics says that absolute zero cannot be reached by a finite number of physical steps. Quantum mechanics also prevents the simple classical image of all motion vanishing completely. At the lowest temperatures, nature does not become boring or still, it becomes more quantum. The contrast with cosmic temperature is striking. The universe's background radiation is about 2.7 Kelvin, a faint afterglow from a hot beginning. Cold molecular clouds in space may sit only a little above absolute zero by everyday standards. Yet laboratories can create much colder systems, not by finding naturally frozen places, but by carefully controlling motion, light, magnetic fields, and energy. In a universe filled with stars, plasma, radiation, and ancient microwaves, some of the deepest cold is made by intelligence arranging matter with exquisite care. This shows how flexible the idea of temperature really is. It can describe the warmth of a hand, the glow of a star, the radiation of the early universe, and a tiny cloud of atoms cooled until quantum mechanics becomes visible. Temperature is not only a comfort scale, and not only a cosmic measurement, it is also a precision instrument. At ordinary temperatures, matter hides much of its quantum nature beneath restless motion. Near absolute zero, that motion quiets, and stranger patterns emerge. The universe's coldest natural shadows may preserve ice and ancient chemistry, but the coldest laboratories reveal something even more delicate. Matter approaching the edge of its lowest possible thermal life, where particles begin to behave less like separate grains and more like one shared wave of possibility. Not every temperature in the universe announces itself with light. Stars glow. Hot gas emits X-rays. Warm planets release infrared radiation. The cosmic microwave background fills the sky with a faint, measurable afterglow. These are difficult observations, but at least they involve radiation that instruments can detect directly. Some parts of the universe are far more secretive. They barely interact with ordinary matter and light at all, which makes their thermal histories much harder to read. Neutrinos are among the best examples. A neutrino is an extremely light particle that interacts through gravity and the weak nuclear force, but not through electromagnetism. That means neutrinos do not reflect, absorb, or emit ordinary light. They can pass through planets, stars, and human bodies with almost no chance of noticing. Trillions of solar neutrinos pass through a person every second, which sounds dramatic until one remembers that they're very polite about it and almost never bump into anything. The neutrino was first proposed by Wolfgang Pauli in 1930 as a way to explain missing energy in radioactive beta decay. Enrico Fermi later developed the theory of beta decay and gave the neutrino its name. For a while, neutrinos were only a theoretical solution to a problem, tiny, invisible bookkeepers carrying away energy and momentum. Then, in the 1950s, Clyde Cowan and Frederick Rines achieved the first direct detection of neutrinos using particles produced by a nuclear reactor. A particle that had once seemed nearly undetectable had finally left a measurable trace. Neutrinos matter to cosmic temperature because they were also produced in enormous numbers in the early universe. In the first seconds after the Big Bang, the universe was hot and dense enough that neutrinos interacted much more often with other particles. But as space expanded and cooled, matter became less dense, and neutrinos stopped interacting frequently. They decoupled from the rest of the cosmic plasma much earlier than the photons that later became the cosmic microwave background. This leads to the idea of the cosmic neutrino background. It is a predicted relic population of neutrinos left over from the early universe, similar in spirit to the cosmic microwave background, but much harder to detect. These neutrinos should fill space today, carrying information from a time when the universe was only about 1 second old. Their present temperature is expected to be lower than that of the cosmic microwave background, roughly just under 2 Kelvin, though speaking of neutrino temperature is subtle, because neutrinos have tiny masses and interact so weakly. Unlike the CMB, the cosmic neutrino background has not yet been directly detected in the same straightforward way. Its existence is strongly supported indirectly by cosmological observations, including the successful predictions of Big Bang nucleosynthesis and measurements of the cosmic microwave background. But actually catching these ancient neutrinos is extraordinarily difficult. They are slow, faint, and reluctant to interact, which is not ideal behavior for anyone hoping to be observed. Modern neutrino science uses remarkable instruments. CERN has played a major role in particle physics experiments involving neutrinos and the weak interaction. Super Kamiokande in Japan detects neutrinos using a vast underground tank of ultra-pure water, watching for tiny flashes of light produced when neutrinos occasionally interact. The Ice Cube Neutrino Observatory at the South Pole uses a cubic kilometre of Antarctic ice to detect high-energy neutrinos from cosmic sources. The Katrin experiment in Germany measures the mass of the neutrino by studying the energy of electrons from tritium beta decay with extraordinary precision. None of these experiments has yet made the cosmic neutrino background easy to see, but together they show how seriously science takes particles that almost never say hello. Then there is dark matter, an even deeper hidden component of the cosmic story. Dark matter does not appear to emit, absorb, or reflect light, but its gravity is visible through the motions of galaxies, the behavior of galaxy clusters, gravitational lensing, and the structure of the cosmic web. It outweighs ordinary matter in the universe by a large factor, yet its true nature remains unknown. It may be made of one or more kinds of particles not yet detected directly, or it may point to physics still beyond current understanding. Dark matter also has a thermal history, even though scientists do not yet know its details. One important question is whether dark matter was cold, warm, or hot in the early universe. These words do not mean comfortable, mild, or in need of a small fan. They refer to how fast dark matter particles were moving when cosmic structures began to form. Cold dark matter would have moved relatively slowly, allowing small structures to form early and merge into larger ones. Hot dark matter, moving close to the speed of light, would have smoothed out small structures more strongly. The success of the lambda cold dark matter model suggests that dark matter behaves mostly as cold dark matter on cosmic scales, though its particle identity remains unknown. This hidden thermal past matters because structure formation depends on motion and energy. If dark matter moved too quickly in the early universe, it would erase small density variations before they could grow. If it moved slowly enough, gravity could amplify those variations into galaxies and clusters. In this way, the temperature-like behavior of dark matter helps shape the architecture of the universe, even though dark matter itself is invisible to telescopes. The universe's temperature story is therefore not limited to what glows. Ordinary atoms, starlight, hot plasma, and the cosmic microwave background are only part of the picture. Relic neutrinos and dark matter carry traces of early conditions that are much harder to access. Some of the most important thermal histories are hidden, not because they are unimportant, but because the universe often stores its deepest clues in things that barely interact. So the question of why the universe has a temperature reaches into unseen territory. It includes visible light, ordinary matter, ancient microwaves, ghostly neutrinos, and unknown dark matter shaped by the early cosmos. The universe is not only warm or cold where it shines, it has thermal memory in particles that pass through worlds, in matter detected only by gravity, and in faint patterns left from when everything was closer, hotter, denser, and stranger than the quiet sky suggests. The universe has been cooling for a very long time, but its future temperature depends on something still deeply mysterious. The expansion of space is not merely continuing, it is accelerating. The name given to whatever is causing that accelerated expansion is dark energy. It is not dark because it is shadowy in the ordinary sense, and it is not energy in the simple everyday sense of fuel, heat, or electricity. The name is a placeholder for something real in the equations and observations, but not yet fully understood. The evidence for dark energy became clear in the late 1990s when two teams studied distant Type 1 supernovae. These exploding stars can be used as cosmic distance markers because their brightness follows patterns that allow astronomers to estimate how far away they are. Saul Perlmutter led one team, while Brian Schmidt and Adam Rees were key figures in another. They expected to measure how gravity was slowing the expansion of the universe. Instead, the distant supernovae appeared dimmer than expected, suggesting they were farther away than they should have been in a simply slowing universe. The expansion was not decelerating as anticipated, it was speeding up. That discovery changed the story of cosmic temperature. If expansion continues to accelerate, distant galaxies that are not gravitationally bound to the local group will drift beyond observable reach over immense timescales. Space between large-scale structures will stretch faster and faster. The universe will become more dilute. Ordinary matter will not vanish, but it will become increasingly isolated in separated islands of galaxies, stars, remnants, black holes, and thin gas. As space expands, the cosmic microwave background will continue to cool. Today, it has a temperature of about 2.7 Kelvin, the faint afterglow of the early hot universe. But the wavelengths of those ancient photons will keep stretching. Their energy will continue to fall. Far in the future, the CMB will become colder, fainter, and shifted to wavelengths so long that detecting it would be extraordinarily difficult. The afterglow will not suddenly switch off. It will fade by being stretched, like a note drawn lower and softer until it slips beneath hearing. Star formation will also gradually decline. Stars form when cold gas clouds collapse under gravity, but galaxies do not have an endless supply of fresh star-forming gas. Over cosmic time, much of that gas is locked into stars, stellar remnants, planets, or expelled and heated by stellar winds, supernovae, and active galactic nuclei. New stars will still form for a very long time, especially small red dwarfs that burn slowly and gently. But the great age of abundant starbirth will fade. The universe will become less bright, not because all light ends at once, but because the processes that make fresh light become rarer. This leads to the idea of heat death, one possible long-term future of the universe. The name sounds dramatic, as though everything freezes in a single catastrophic moment, or the cosmos suffers a theatrical final curtain with excellent lighting. But heat death is not an explosion, and it is not a sudden, icy event. It is a slow, thermodynamic fading over timescales so vast that ordinary imagination has very little to grip. Heat death means a state in which usable temperature differences become increasingly rare. Energy becomes more evenly spread. The gradients that allow work, structure, and change become weaker. Temperature differences matter because they drive processes. A star shines because energy flows from a hot core toward cooler space. Weather happens because sunlight, atmosphere, oceans, rotation, and surface conditions create contrasts. Life uses energy gradients, taking in useful energy and releasing waste heat. Engines work because heat flows from hotter regions to cooler ones. When temperature differences disappear, there is less usable energy available to do work. The universe may still contain energy, but not in forms that can easily create new structure or activity. Heat death is therefore not the end of existence in a simple sense. It is closer to the end of useful contrast. Stars would eventually exhaust their fuel. White dwarfs would cool. Neutron stars would fade. Black holes would remain for astonishing durations, slowly interacting with their surroundings and, in principle, losing energy through Hawking radiation over immense spans of time. The universe would become darker, thinner, and quieter. Not empty all at once, but increasingly unable to organize energy into bright, complex, changing systems. Dark energy makes this future especially stark if it behaves like a cosmological constant, the simplest current explanation. A cosmological constant means dark energy retains a constant density as space expands, causing expansion to accelerate forever. In that case, distant structures become increasingly unreachable, and the observable universe slowly empties out from the point of view of any remaining observer. Other possibilities exist, because dark energy is still not fully understood. Its nature could be more complicated than the simplest model. But the best current evidence is consistent with an accelerating universe dominated by something very much like a cosmological constant. This connects directly to cosmic temperature. The future thermal state of the universe depends on expansion, gravity, star formation, black holes, and the large-scale behavior of space-time itself. Expansion cools radiation. Gravity gathers matter and creates local heat. Stars transform nuclear energy into light. Black holes connect temperature to horizons and quantum fields. Dark energy shapes how far and how fast the cosmic stage stretches. So the temperature of the universe is not only a record of its past, it is also a clue to its future. The universe began hot and dense, then expanded and cooled. It formed stars, planets, galaxies, clusters, and all the warm local exceptions that make the cosmos rich and uneven. But if accelerated expansion continues, the long trend points toward thinning radiation, fewer new stars, weaker usable gradients, and a colder, quieter future. Not a dramatic ending, but a slow fading of contrast as the universe stretches its remaining warmth across an ever wider dark. Temperature began here as something familiar. Warmth in a mug, cold glass beneath a fingertip, a blanket slowly collecting heat in the dark. But followed carefully, that simple sensation opens into almost everything. Temperature connects the invisible motion of atoms to the glow of stars, the cooling of planets, the faint radiation between galaxies, the strange thermodynamics of black holes, and the far future of the universe itself. It is one of the quiet threads running through physics, from the smallest particles to the largest cosmic scales. At the particle level, temperature describes motion and energy. Atoms vibrate in solids, slide and flow in liquids, and move more freely in gases. Kinetic theory, shaped by the work of James Clerk Maxwell and Ludwig Boltzmann, showed that heat is not a magical substance hidden inside matter, but a statistical pattern made from enormous numbers of moving particles. A warm object is not filled with warmth in the way a cup is filled with water. Its particles simply have more average thermal energy than they would in a colder state, but temperature does not stop with matter. Light can carry a temperature too, when radiation has the pattern of thermal equilibrium. Blackbody radiation, explained by Max Planck, shows how the colour and spectrum of light reveal the temperature of the source. Cooler objects emit mostly infrared radiation. Hotter objects glow visibly. Stars reveal their surface temperatures through their spectra. The universe itself left behind a thermal glow, stretched by expansion into the cosmic microwave background known as the CMB. This is the central anchor of the entire question. The CMB is the measurable afterglow of the early universe's hot beginning. It was released when the universe became transparent, roughly 380,000 years after the Big Bang, after electrons joined atomic nuclei to form neutral atoms. Before that, light scattered constantly through a hot plasma. Afterward, photons could travel freely. As space expanded, those photons stretched into longer wavelengths and cooled. Today, the CMB has a temperature of about 2.7 Kelvin, only a little above absolute zero. So when science says the universe has a temperature, it is not claiming that space is one enormous room with a single thermostat. The universe contains many thermal environments at once. The core of the Sun reaches roughly 15 million Kelvin, where nuclear fusion transforms hydrogen into helium. Cold molecular clouds can hover only a few degrees above absolute zero. The thin plasma between galaxies and clusters can reach tens of millions of Kelvin, while still being so diffuse that it would not feel hot in an everyday sense. Large black holes have temperatures so tiny that they are colder than the cosmic microwave background. Ultra-cold laboratories can cool atoms to billionths of a Kelvin above absolute zero, colder than most natural places in the universe. These differences are not contradictions, they are the point. Temperature depends on what is being measured. Matter, radiation, sparse particles, a planet's surface, a star's core, a black hole horizon, or a carefully trapped cloud of atoms. The universe is not thermally simple because it is not physically simple. It contains energy distributed through matter, light, fields, relic particles, and perhaps unknown forms of matter such as dark matter. That energy is shaped by expansion, gravity, quantum mechanics, nuclear fusion, electromagnetism, and thermodynamics. Planets show how local temperature becomes a balance. A world absorbs light from its star, reflects some away, and emits infrared radiation back into space. Atmospheres can trap some of that outgoing radiation through the greenhouse effect, involving gases such as water vapour, carbon dioxide, methane and ozone. Surfaces, clouds, oceans, rotation and internal heating all matter. Venus, Earth, Mars, the Moon, Pluto, Titan, Europa and Enceladus all remind us that distance from the Sun is only one part of the story. Temperature is always a conversation between energy gained, energy lost, and the materials doing the negotiating. Stars show another part of the story. They are local furnaces inside an overall cooling universe. Gravity gathers gas into dense regions. Pressure and temperature rise. Nuclear fusion begins. Arthur Eddington helped recognise that stars could be powered by hydrogen becoming helium, and Hans Bethe explained the nuclear pathways that make that possible. A universe whose background radiation is cooling can still create blazing stars because gravity concentrates matter and fusion releases stored nuclear energy. The cosmos cools on the larger scale, yet continues to make islands of heat. Black holes make the idea stranger still. Jacob Bekenstein connected black holes with entropy, and Stephen Hawking showed that quantum effects mean black holes can be assigned a temperature and can emit Hawking radiation. This does not make ordinary black holes warm in any useful sense. Stellar mass and supermassive black holes are extraordinarily cold by this measure. But the idea itself is profound. Temperature reaches even into horizons, entropy, quantum fields, and gravity. The hidden universe has its own thermal traces too. Neutrinos, first proposed by Wolfgang Pauli and later detected by Clyde Cowan and Frederick Rains, may exist today as a cosmic neutrino background, a relic from the universe's first seconds. Dark matter, still unidentified, may carry clues in its own thermal history, because how fast it moved in the early universe affected how galaxies and clusters could form. Not every temperature shines. Some are inferred from gravity, particles and structure. This is why temperature reveals history. It tells us what matter is doing now, but also what it has been through. A star's temperature speaks of fusion. A planet's temperature speaks of atmosphere and sunlight. The CMB speaks of a time when the universe was hot, dense, and newly transparent. Cold laboratories reveal quantum behavior by removing thermal noise. Hot gas between galaxies reveals the power of gravity to turn falling motion into heat. Even the possible heat death of the universe is a temperature story where usable differences may slowly fade over immense time. A simple sensation becomes a cosmic record. Warmth is not just comfort. Cold is not just absence. Temperature is motion, radiation, memory, contrast, and change. It is one of the ways the universe carries its past into its present, and one of the ways its future can be imagined. From the first visible light to the last fading stars, from a cup cooling quietly beside the bed to ancient microwaves crossing the dark, temperature is the universe telling the story of where its energy has been. So the universe has a temperature because it has never been empty of energy. It has particles in motion, radiation crossing space, stars gathering matter into fire, planets absorbing and releasing light, and ancient photons still travelling from the time when the cosmos first became transparent. Temperature is not only something felt on skin or read from a thermometer. It is a way of describing how energy is arranged, how it moves, and how it changes with time. The universe began in a far hotter and denser state than the one seen today. As space expanded, radiation stretched to longer wavelengths, particles became less crowded, and the great background glow cooled. That cooled remnant is the cosmic microwave background, the CMB, now only about 2.7 Kelvin, yet still carrying evidence of the early universe's heat. But the cosmos is not simply cold. Stars still shine. Planets keep and lose warmth in their own delicate balances. Thin plasma between galaxies can reach tremendous temperatures. Black holes carry the strange idea of horizon temperature. Frozen shadows on moons and planets preserve deep cold, while laboratories on Earth can create conditions colder than nearly anywhere in nature. The universe is not one temperature. It is many thermal stories unfolding at once, and through all of them, temperature reveals history. It shows where energy has gathered, where it has spread, where matter has changed form, and where time has left a trace. It is part of the arrow of time, the slow movement from concentrated beginnings toward wider, quieter distributions of energy. So the universe is neither simply hot nor simply cold. It is an immense evolving system, filled with contrasts, remnants, furnaces, shadows, and whispers of old light. Even empty space carries memory, not as words or thoughts, but as stretched and cooled radiation still moving through the dark, a faint warmth left behind from the beginning of everything.